Hello, everybody. Thanks a lot for coming here. I know somebody of you came from very, very far. And it's my pleasure to introduce you the chief of my department of mathematics, who wants to welcome you directly. Professor Giacomo De Marco. I forgot to tell you.
Okay, so good morning, everybody, esteemed colleague and fellow mathematician. Well, for me, it's both an honor and a privilege to welcome you to this Hopf Algebras and Monoidal Categories conference, which we held in this beautiful and historic city of Ferrara. My name is Giacomo Di Marco, and I'm delighted to be addressing you today, not only as a colleague, but also as the future director of the Department of Mathematics and Computer Science of our university. It is a great privilege for me to be part of such a high-level academic community, and I look forward to continuing our department's long-standing tradition of excellence in research, teaching, and innovation. So before we begin, I would like to extend the warmest greetings on behalf of our rector, Laura Romacciotti, who unfortunately could not join us today due to prior academic commitments. She sends her best wishes for accessible and productive conference, and we are grateful for her continued support of our department and its endeavors. So this conference holds a special significance as we honor a remarkable colleague, Professor Claudia Menini, who will soon, unfortunately, be retiring. Claudia has worked at the University of Ferrara for over 40 years, almost her entire academic career. During this time, she has become one of the most respected figures in our field and is currently the dean of our university. Many of you here today have had the privilege of collaborating with her, whether in research, teaching, or, well, department initiatives. Her very big contribution to the field of algebra and category theory have been pivotal, especially in the area of algebras. Her work has inspired many of us, both as a colleague and as a researcher. Claudia's passion for mathematics, her dedication to teaching, and her generosity as a mentor have left an indelible mark on our academic community, as well as on the very large number of students she has guided over the years. We are here today not only to explore mathematical concepts, but to celebrate her contribution to the field and her remarkable career. Ferrara, as many of you may know, is not only a city rich in history and culture, but also a UNESCO World Heritage Site, known for its Renaissance architecture and vibrant intellectual past. Ferrara has long been a center of learning and creativity. The University of Ferrara embodies this spirit, making it the perfect host for this congress. Mathematics, as many of you may know, mathematics, as we all know, is more than just numbers, equations, and theorems. It's the foundation upon which countless scientific discoveries are built, and has been the key to unlocking many of humanity's greatest achievements, from technology, engineering to economics, and even arts. The study of algebraic structure, like Hopf algebras and monoidal categories, represents some of the most profound and exciting direction in modern mathematics, with application ranging from quantum groups and topology to theoretical physics. In today's world, where data, algorithms, and computation are driving innovation at an unprecedented pace, the role of mathematics is more essential than ever. Our work as mathematicians extends far beyond the classroom, influencing industries, shaping policy, and solving real-world problems. This Congress is an opportunity for us to reflect on our collective progress and to look forward to the future of mathematical research in this dynamic field of algebra. Over the next few days, we will be fortunate to hear from some of the leading voices in Hopf algebras and monoidal categories, explore new advancements, and foster collaboration that will inspire us to think critically and, I hope, creatively. And when we are not engaged in deep intellectual discussion, I hope you take the opportunity to explore Ferrara's charming street, visit the Castello Estense, and experience the rich history of our university. I encourage you all to take full advantage of the session, engage with your fellow participants, ask questions, and most importantly, be open to new ideas and perspectives. It is in this conversation and collaboration that our field grows and the magic, in some sense, become reality. In closing, I would like to extend my gratitude to the organizing committee and, of course, to the University of Ferrara for hosting us. Most of all, I would like to express our deepest appreciation to Professor Claudia Menini, whose contribution to mathematics and algebra has been very important over this year. Claudia, on behalf of all of us, thank you for everything. And thank you all for being here. Let's make this Congress and success, and most importantly, well, enjoy the week and the journey of discovery. Welcome to Ferrara, and let's the conference begin. Thank you, everybody. So next, who is going to present?
Right, so hello everyone. It's time to start mathematical proceedings of this conference. And it's a pleasure to introduce the first session. Particularly, it's a conference celebrating achievements of Claudia, who has just left, I think. But anyway, I know her for many years, and I remember well the conference which was here in Ferrara 20 years ago. It was my first visit to Ferrara. It was a flying circus of Hopf algebras coming from Canada to Ferrara and then to Swansea. And among those flying members of this flying circus was Steph Canepel, who will give the first talk today. The title is Multimonads in Two Categories. Steph, over to you.
So, okay. Thank you very much for this nice introduction. So my first visit to Ferrara was not, I was here in 2004, but I was here much earlier, in 1990, and this was also an important event. There was a meeting on commutative algebra in Bressanone, and I went there together with Fred, but before going to Bressanone, we first flew to Venice, and then came to Ferrara, where we met Claudia and other legendary persons like Mario Fiorentini. And in Bressanone, that was also very important. This was a surprise. There were 7 Romanian mathematicians there. And before that event, I met only one Romanian in my whole life, and that was Constantin Nastasescu. And this was the start of a fruitful cooperation between Flemish and Romanian mathematicians. Now, Claudia has organized many nice conferences afterwards here in Ferrara. The one in 2004 was legendary, and I have to tell you an inside joke about this. When I retired 3 years ago, shortly after that, there was also some kind of celebration in my faculty, and the dean, who is not a mathematician, gave a speech and showed some pictures, and one of the things he mentioned, and some of you will remember what it was, he mentioned the cuckoo bottle. For those of you who were not there, I will tell you what this was, but this was something naughty that we did. Okay, the title of my talk is Multimonads in Two Categories. So let me first briefly introduce what the two categories. Well, the main idea is like a category consists of objects. I denote the objects by small letters. And then for each couple of objects in a category, you need a set. In a two category, you need a category. And I denote it so the category of from B to A, so B is there, the origin. I denote the origin at the end, which is more convenient for the notation afterwards. And then you have a composition. This composition has to be functorial. And the objects in all these categories are called one-cells, and they are denoted by capital letters. And the morphisms are called two-cells, and they are denoted by Greek letters. Now, the notation. So the composition of one-cells I denote as a tensor product based on a particular example that I will show in just a second. And the tensor I delete very often as it is not needed. And the same notation for two-cells. The unity on a one-cell or on a two-cell is denoted by the same letter as the one-cell or the two-cell, and composition of the two cells by the usual notation. The basic example is that of categories. The objects are categories. One cells are functors, two cells are natural transformations. Second one, we work over a field or a commutative ring, and as objects you take K algebras. One cells are bimodules and two cells are bimodule maps. So that is the inspiring example for me. And then, as we all know, a strict monoidal category is a two-category with one cell. With one zero cell, I'm sorry. Maybe I mentioned this, you can also introduce bicategories, and the bicategory with one zero cell is a usual monoidal category, and there's also a coherence theorem, and this is why I restrict to two categories. Another example, which is not so commonly known, is the following. You take a strict monoidal category, and you take a class. And then we can form a two-category, and the objects are the elements of the class, or of the set, if you want to avoid logical foundation problems. And then for all couples of objects in the class, the connecting category is just the strict monoidal category. So this is some kind of rectangular construction which will be important in the sequel. Now, it was observed already a long time ago by the founder of the subject, Ben Abou, that in a two-category you can define many things that we know from algebra. You can define adjunctions, you can define Morita contexts, you can define Frobenius pairs. These are adjunctions that are at the same time left and right adjunctions. You can define monads and comonads. You can also name them monoids and comonoids, or algebras and co-algebras, depending on where you come from. And then Frobenius monads, which are monads and comonads with an appropriate compatibility condition. Now, one of the things that I was wondering not so long ago about is the following. So monads you can define, but if you look at a monad, and there the basic example is monads in the two category of categories. So there you need basically one basic category and an end of functor. So this is only one category that you consider, so you don't need the whole two category of categories. And the question is there some multi-objected version of this, where you eventually can, if you want, even use all the objects of the two category. And this is what I call a multimonad. So what you do is, you take a class of objects, you can take all objects if you wish, and then you need, for every couple of objects, you need a one cell, AAB, which is a one cell going from B to A, which I denote by AAB for the convenience of notation, as I already mentioned. Secondly, you need some multiplication maps, AAB, ABC to ABC. So you see the indices are working better if you use this notation, AAB instead of ABA for things going from B to A. And then for each object A in A, you need a unit 2-cell from A to AAA. So these mu and eta are 2 cells. And the notation that I use, you can mention all the indices, but usually I omit them. And in the notation, the unit and the multiplication maps are sometimes also deleted. And then you need some axioms that you can guess, associativity and unit. And I will come back to that later. It is very similar to what you meet in enriched category theory. I will come back to that in a second, because this will turn out to be a generalization of this. So this is the first thing, of course. If you take X to be a singleton, then you recover the classical notion of a monad. And then, this is something which might be a little bit surprising. So consider a Morita context. I used already appropriate notation for the connecting modules and maps. In fact, 1 cells and 0 cells in an arbitrary 2 category, but you can do this in bimodules if you want. And then, so you have 1 cells going from A to B and from B to A, but you need also 1 cells from A to A and from B to B, and you take for those ones the trivial ones. So you take the unit 1 cells. And then for eta A, you have only one possibility, that is the identity on A, and for eta B the same. And then there are several multiplication maps that you need, and you also take the identity for this, where you identify small a times capital A with A itself, because you work in the strict context. So then it turns out that you obtain a multimonad with 2 objects. And conversely, if you have a multimonad with 2 objects, but where the 2 auto objects are the trivial ones, then a Morita context follows from this. So there is a connection with Morita contexts. And then a third example is the following. You can consider a strict monoidal category, and you consider a class or a set, if you are cautious. And then you can consider, I mentioned already, the 2 category Vx, where the objects are X, and all the 1 cell categories are the basic category V. Then it turns out that the multimonad on X is just a V category with X as class of objects. So what we have here is, if you want, a generalization of an enriched categories. Another example, so it is well known that you can construct monads from adjunctions. There's a similar result in the multi setting. You fix one object, and then you fix a class. The object E does not have to be an object of the class. And then you assume that you have adjunctions between this fixed object and every object of the class. Then what you do is you take MAE, MEB from the adjunction, so from 2 different adjunctions, and you can compose them because the inner index is equal to E, and that you call AAB, and then the multiplication is obtained by inserting the co-unit of the appropriate adjunction, and for the unit you take the appropriate unit of the adjunction, and you obtain a multimonad. So that seems to work well. There's an alternative definition that you can give, which is a little bit more categorical. What you can do is you can consider the trivial 2 category, namely 1 0 cell, 1 1 cell, and 1 2 cell. So basically you have one object, and then for the 1 cell, you take the discrete category with one object. And then you can take a class, and then you take 2 to the x, which is a special case of the v to the x that we just considered. This 2 is a strict monoidal category. So as I indicate there, so the 1 cell categories are discrete categories with one object E, A, B, and then with the obvious multiplication. So I could draw this on the blackboard, so you get discrete categories, and all with one arrow you can make a picture of that. And now if you take, where you take X, a subset of the objects, and then it turns out that a multimonad is just a lax functor from this 2 to the x to A, where you impose that A of A is equal to A. So this is a functorial definition. And this goes back to an observation that was made by Benabou. A monad is a lax functor from 2 to A. Okay, so this is all well, but what can we do with this? There are 2 things that I want to talk about, if I have the time. The first thing is the following. There are 2 papers, the formal theory of monads 1 and 2. The first one written by Street already in 1972, and the follow-up by Steve Lack and Ross Street in 2003. And there, what they do is they show that monads can be organized into a 2 category. And actually there are 2 versions of this. There's the 2 category monads, and the Eilenberg-Mohr 2 category. And the difference is in the 2 cells. The 0 cells and the 1 cells are the same, but the EM has more 2 cells, and it's in such a way that there is a 2 functor from one to the other one. And there is another one related. This is called the Kleisli 2 category, mentioned in one of the papers, but this is basically the same construction as the Eilenberg-Mohr 2 category by using opposite arguments, and the opposite is here in the 1 cells. And this is the one that I will come to. There's another thing, and that you can find in the book of Max Kelly. If you consider all V categories, they can also be organized into a 2 category that is called V-cat. And the 2 constructions, the one of Lack and Street and the one, it is in Kelly's book, but I don't know whether Kelly was the original author of that. It is not clear at the first glance whether there is a relation between both of them. Can we do such a thing with multimonads? And this turns out to be the case. I will explain the construction. It is, of course, a little bit more complicated because of all these indices that we have. So we take 2 multimonads with different underlying classes. That is allowed. And then you need, for convenience, take sets for the classes. Then you need a function from x to x prime. Then a 1 cell from A to FA for every A in X. And then a 2 cell, phi AB. And you would expect that that would go from AAB to A prime FA FB. But that is, the dimensions do not fit. This is something that you can see in the construction of street already. So you need what the dimensions fit if you go from UA, AAB to A prime of AFB, UB. And then that is in the category from B to FA. And so these are the data. And then you need axioms. There's one involving the multiplication. So what you can do is you can consider the multiplication AAB, ABC, and with the UA in front, you can apply the multiplication on the right-hand side and then a phi. And then what you also can do is you can apply 2 times phi, and then multiplication, but the multiplication with a prime. The diagram has to compute, and a similar one respecting the units. Okay, and then you also need to describe the identity and the composition. The identity, okay, so there you take, you need for the function, you need the identity function. The UAFA, you take the trivial small a, and then the AAB, you take the identity where you identify A times AAB with AAB times B using the strict setting that we work in. And composition is then a little bit more complicated. I won't go into the details because I want to go to the second subject, and you can define 2 cells also. And there's an axiom for the 2 cells given by a diagram that you can see here. And the composition of the 2 cells you also need to define. It's not immediately obvious, but after you discover it, it turns out to be the natural things. So this gives us a 2 category, which I denote MM. This stands for multimonads. Okay, what is the relation to the previous constructions? Well, the first thing is, so if you consider the full sub-2 category, where you consider classes that are singletons, so that the 1 cells are monads, then you obtain precisely the Kleisli 2 category. And if you adapt the construction, reversing some arrows, you can find the Eilenberg-Moore construction also. And this explains something. So there was also the monad construction, which appeared in the first paper by Street, generalized to the Eilenberg-Moore construction. If you look at the 2 constructions, at first glance you think the monad construction is the most natural ones. Well, looking at the more general setting, it turns out that this is maybe not the case, because if you look for a generalization to the multi-setting of the monad, you don't find it because of dimension problems. What I can also remark is that recently there has been a renewed interest in this Eilenberg-Moore categories in special settings, with development of theory of reads and co-reads, as was done. I was involved in this, and Daniel Bolaco and Blastovic, Ilias, and others. So this is the first connection. This is the construction. Then an observation. I won't go into the details. You can spell out the details, but it turns out to be something quite complicated if you write it out. You can organize Morita context into a 2 category. I don't know whether that has been observed before. Now, we look at V categories. So as I mentioned, they can be organized into a 2 category. This 2 category is not precisely the construction that I gave, but you can reduce it to it. So if you consider 2 V categories, which are, as I explained, multimonads, so you can consider a 1 cell, 3 sets of data. So this use UA has to be a 1 cell from A to FA, But in the enriched setting, all these categories are equal to V. So you can say, okay, we look at one cells where this UA is equal to the identity object of V. Then the phi AB goes from AAB to A prime FA FB. Then it is possible. And if you consider a two-cell, then that turns out to be just a V-natural transformation. So what is the conclusion? That is that the two category of V categories is the two category that arises by restricting the one cells to ones of the type F, I, phi, and then once you restrict to these one cells, the underlying two cells are the same. You can also introduce morphisms. If you take x and x prime equal, and then you can impose that the function from x to x is the identity, and then you can obtain what you call classical morphisms. And here this explains also why it is maybe more natural to look at the Kleisli construction than the Eilenberg-Moore construction, because then that is what you want in the algebraic setting, a function from A to A prime, and otherwise you get it in the opposite direction. That is not really what you want. You can generalize the notion of algebra. This is the algebra notion in the categorical setting. There you can also play with the objects. You take another class, and then you take object of the form MYA, and then some action, and with the obvious associativity and unit conditions that I will not. And it seems likely that you can do some two categorical constructions where y is variable. This I did not investigate, but you can define morphisms if you keep y fixed. Now, in the case where you look at classical monads on categories, then you can define a T-algebra. This seems to be not the same from the dimension point of view, because there you need a map from TC to C, where C is a category, where C is an object in the category. But the category itself corresponds to functors from the trivial category to the category, and then this matches with our definition if you take a singleton and singleton, the trivial singleton for the set Y. Okay, and this explains also why this theory of algebras of classical monads is one-sided, because you can do this only from one side. Obviously, you can introduce multi-comonads. I will go quickly over it, because otherwise I cannot say. And then what you can do is you can introduce Frobenius multimonads. So these are multimonads and multi-comonads with an appropriate compatibility between multiplication and co-multiplications, which I have here. I have very few time left, so I will go quickly over it. This was already investigated for V categories by Mitch Buckley, Timmy Viermans, Christina Vasilakopoulou, and Joost Verkruijsen in two papers that appeared recently. Okay, you can introduce Frobenius systems. So, given all the structure maps, you can introduce two additional ones. They are in two indices, but I write three indices for the convenience of notation. You take an eta first, and then you apply an appropriate co-multiplication, and then you obtain iota, and there's a theta in a similar way. This iota is a generalization of the Casimir elements in a Frobenius algebra. And then there are several formulas. And then one thing that you obtain, and that's maybe the most important, if you have such a Frobenius multimonad, then you have a lot of adjunctions. Namely, between every couple of elements in the underlying class, you have an adjunction, and for this you need the iota and the theta. And you can reformulate the axioms using this iota and theta. You can take iota, and if you know iota, then you can recover delta. This is one of the formulas on the previous slides. And the same thing for the multiplication. If you know theta and all the other structure maps, you can recover the multiplication. And this gives you equivalent description of Frobenius multimonads, which is something that was known for Frobenius monads before, but you have to adapt it. A few properties that I checked to finish that are well known for Frobenius algebras that can be generalized. If you have a Frobenius multimonad, you can you fix a class Y, and then you can look at categories of algebras and categories of coalgebras. These categories are isomorphic. This is a sketch of proof, but I don't have time to go over it. Another one, if you have a morphism between Frobenius multimonads, so this has to be a morphism of monads and of comonads, it's automatically an isomorphism. And here, sketch of proof, here the inverse is constructed. Finally, we know that a Morita context yields a multimonad. It is exactly a Frobenius multimonad if it is a strict Morita context. And then finally, I have indicated that you can obtain multimonads from sets of adjunctions. Well, if you have a second set of adjunctions, but then in the other direction, not from A to E, but from E to A, so left, right changed, then you can construct a multicomonad. And in the situation, so where you have Frobenius pairs, so from A to E, so left A and right A, but with different units and co-units, then you obtain a multimonad. And as a corollary, if you have a Frobenius multimonad and you fix one element in E, you can take that element E, and then you can construct a new Frobenius multimonad, taking EAB is AAE, AE, BE. And you can do that for every E, so there is then maybe finding explicit examples is not so obvious, but here is a construction that once you have one, you can obtain as many as you want. Okay, and this is the end of my talk.
Thank you very much. Any questions? Yes, please. Can you wait a second? So I will explain that there is only one mic. So you will tell the question, I will repeat it. So that's for the benefit of the people watching online. Okay? So sorry about that. And if you could speak up, please.
There's already a notion of multimonad introduced by ECA in 1980, and I think it's not related to yours, just a class organization. But did you know that there is a function?
Okay, so I will repeat. The question is that in the literature there is a notion of multimonad, and how is it related to what we're talking about?
Okay, so this is one of the things that I was wondering about when, so there were two things. One of them is choosing the right terminology. So if there is already something, then maybe you have to change the terminology. That is one thing. The other thing is, of course, I have been wondering, and so some people have experienced this, there is a huge amount of literature on category theory, but it is not always accessible to everybody. So the community of category theorists, there was a period where they were just exchanging their papers in their own circle, and it's not always easy to find them. So it's not so. So when I introduced this notion, I thought maybe somebody already thought about this possibility. So it could be, I don't know. So, but you have to give me the reference.
It's the multi-adjunctions and multimonads. It's a paper from 1980. A multimonad in essence is a category with a discrete vibration on it, and the monad on the domain of the discrete vibration.
Okay, I will look at it and see if there is a connection. And you know the name of the author? Okay. Thank you. If you can write it, that would be nice.
Any other questions? Yes, please.
Perhaps it's related to the other question, but you have the notion of multimonad on X, where X is a class of objects in a true category. Right?
Yes.
Is it possible to view multimonads on X as honest monads on a new true category?
I don't think.
So let me repeat the question. So the question is that the definition of your definition of a multimonad is defined on the category X, and whether it's possible to do it as a definition of a monad on multi-category, right? Or have I missed?
Change the two categories to a new one so that monads in the new one become.
Okay, to change the category to category into a new one so that the multimonads become monads.
If that would be the case, then enriched categories also would be a special case of monads. And I haven't seen that in the literature. So I doubt it. But it could be, of course.
This is true for the other notion.
Enriched categories are monads.
But it's not true for categories enriched over a monoidal category, I think. Because there is, once you have multiplication, so if you have one object, 1 times 1 is 1, but if you have n objects, n times m is n times m, it's difficult to get that into one thing, I believe.
Any other questions? Yes, please.
Maybe a short question. Do you think about a operatic description of multimonads?
No.
So is there an operatic description of multimonads?
I haven't investigated it. There are still many things that need to be investigated. So
Right.
one of the things, for example, this might be interesting for you. So you have multi-comonads. If you do that in bimodules, then you will obtain multi-corings. And corings have been studied extensively by Thomas, by myself. So there is very illuminating theory, Galois theory for corings. Maybe there is something, but I thought about it yesterday on the plane. That might be a possibility, but it still has to be worked out. So there's a lot to do.
Okay, so I think it's time to thank the speaker again. And we start in, well, as soon as possible. Right, the second talk is given by Kenny Brown, who introduced me to a very nice Isla malt, Hopf. Unfortunately, he will not be talking about whiskey, but fortunately, he will be talking about twisted unipotent groups. Over to you, Kenny.
Thanks very much. So it's a great pleasure to be here in Ferrara. This is my first time ever in Ferrara. In fact, the last time I was in Italy, this is really embarrassing, was I was 17 years old, hitching with a friend south as far as we could go. We got to Milan and then we ran out of money and we had to cross the road and head home. So anyway, it's very nice to be here again, and especially nice to be honouring Claudia. I've known Claudia for many years. We bonded as much over the years with running as with mathematics, and talking to her already this morning, I know that we're both still running. In my case, only just, but anyway, still managing to keep going. I hope to run on the walls here in Ferrara at some point this week. Anyway, so this is joint work with Shlomo Galaki. By the way, I find it very hard to give a talk sitting down, so if I move about, yeah, it's really...
Professor, sorry, can you change the chair for, because...
it's squeaking. Yeah, I was aware of that.
It's not useless.
Okay. Great. And I'm higher up as well. So right, plan. So the real guts of the talk, part 3 and 4, 1 and 2 are just background. Many of you will know the background already. If you don't, it's going to be a bit hard because there's a lot of definitions. You can just kind of ignore them and treat it as a black box. And when we get to 3 and 4, it gets kind of specific to Hopf algebras. So the history of this goes back a long way. Twists are sometimes called Drinfeld twists, and they were introduced by Drinfeld in the early 80s, at the very beginning of quantum groups. And this program of investigating twists for Hopf algebras really started with a Russian called Movshev about 1993, who investigated twists of group algebras of finite groups. And then since then, it's been principally carried forward by Ettinghoff and Galaki, looking at coordinate rings of algebraic groups. And this talk I'm going to give is part of that Ettinghoff-Galaki program, really. But I'll say a bit more of the motivation later on. So, first of all, we talk a bit about what is a twist. So for that, we need this concept of a Hopf-2 cocycle, which is a convolution invertible bilinear map from the tensor product of a Hopf algebra H with itself into the ground field. It says K there on the slide, but basically K is just the complex numbers. In fact, I think later on in the slides, it actually drifts into explicitly being the complex numbers. And there's a couple of conditions, the cocycle condition there and a kind of normalization condition on these Hopf-2 cocycles. And these are the gadgets we use to perform these twists. And mainly we'll be entirely actually, we'll be working with an affine algebraic group G, and H will be the Hopf algebra of polynomial functions on G. And then we call J a Hopf-2 cocycle for G in that case. So let's take a Hopf algebra H and a 2 cocycle J for it. Then what we can do with it is construct a new Hopf algebra. The reason it's called JHJ there is because there's a sort of one-sided version of that, which I'll ignore, but this is the two-sided version. And what happens is we keep the same vector space, H, and we make a new multiplication on that vector space. And the new multiplication map is defined there for two elements A and B of H. And if you think of it as just conjugation by J inside the convolution algebra, that's all that's going on. The multiplication is being conjugated by the two cocycle. And this has this miraculous outcome that you can leave the coalgebra structure completely unchanged on the vector space, and you have an antipode, and you have a new Hopf algebra with a new multiplication. Okay. Cotriangular Hopf algebras. What's the point about these? The point is if you start with a cotriangular Hopf algebra and do one of these twists, you keep the cotriangular structure. So, and this is part of the motivation for these twists. It was already part of the key part of Drinfeld's motivation. So to tell you what a cotriangular Hopf algebra is, we need this concept of a convolution invertible map R called an R form for H, which is a bilinear map from H tensor H to C that has these horrible conditions, if you've not seen them before. The key one to look at if you've seen this for the first time is number 2. Number 2, if you think about it, if you take the right-hand side of that identity and move the R over to the left, R inverse, remember it's convolution invertible, then what you're really doing is saying that the opposite multiplication on the Hopf algebra is just a conjugate by R of the multiplication you first thought of. So R has a kind of a conjugation from the multiplication to its opposite side. And number 3 is just saying that remember it's convolution invertible, and the inverse has a very nice form. It's just kind of the reverse, the twist of the original R form. And key thing, if we want to start with a cotriangular guy and twist it and keep cotriangular, we need to know that we're cotriangular to start with. And the point is going to be here, as it says on the last line there, if you start with a commutative Hopf algebra, then epsilon tensor epsilon satisfies these axioms for an R form. So your commutative Hopf algebra is automatically cotriangular. This slide just says you apply J and you keep cotriangular. So you start with, we don't know yet, but some of you do, I hopefully do, know why should we study cotriangular Hopf algebras, but we're coming to that on a slide or so. But anyway, here's the transformation rule. You just basically conjugate your R form for H by J, as in the displayed equation there. And you get R upper J is an R form for the twisted algebra, JHJ. And so the new twisted algebra is still a cotriangular Hopf algebra. And so, as I said at the beginning, we're really going to be doing this starting with our H being the coordinate ring of an affine algebraic group, O of G. And remember, on the previous slide, I said that epsilon tensor epsilon is an R form when H is a commutative Hopf algebra. So we can start with O of G with epsilon tensor epsilon, and then if you apply that equation in the middle of the box with R being epsilon tensor epsilon, you just get J21 to minus 1 starred with J, as in the last line on the slide. Okay, so that gives you a new R form on your twisted guy. So here's the point about cotriangular Hopf algebras. So a tensor category by definition is symmetric if it's braided and the inverse maps are just the reverse map CYX. And so the theorem, which I guess goes back to, well, I'm not sure if it's really, it's stated in this form in the four-author tensor category book, Etinghoff, Galaki, etc. But they don't actually prove it. They say the proof is just the same as the finite dimensional case. So I'm not sure if it's explicitly proven anywhere in the literature. But anyway, HR, a cotriangular Hopf algebra, C its category of left comodules, then the C is a symmetric tensor category with braiding given by that rule there. Basically, we're applying the comodule maps, rho x and rho y, and then hitting the Hopf algebra in the tensor product with our R form, and then twisting. And conversely, this is kind of maybe the surprising part of the theorem, any symmetric structure on C arises in this way from a cotriangular structure. The point is, you don't just get any cotriangular structure, you get one which is naturally equivalent to the one you start with. So this is a motivation for people working in tensor categories. This is a prime motivation for looking at cotriangular Hopf algebras. It's a way of, in the jargon of tensor categories, you get a different fiber functor to the category of vector spaces, but the same symmetric structure on C, naturally equivalent symmetric structure. So we're interested, for those reasons, in this is kind of one direction of motivation from the point of view of tensor categories, understanding all these twisted forms of a given category of comodules, a given Hopf algebra. The motivation that I may be more interested in than that is coming from Hopf algebras, because you get a lot of very interesting new Hopf algebras by performing this operation. And that's what I'm going to try to show you a little bit about in the next part of the talk. Okay, yeah. Whew. Is that about halfway, Thomas? Yeah.
No, we still have more or less 20 minutes.
20 minutes, okay, okay, that's good. Any questions so far? We kind of change topic a little bit here. Everybody okay? So, okay, homing in on unipotent groups now. So H is going to be O of G, where G is a unipotent complex affine algebraic group. So that just means you take strictly upper triangular matrices of some size, T by T, and then you take a closed subgroup of that group of upper triangular matrices. And if it has dimension n, then the coordinate ring is just polynomials in n variables. So as an affine variety, it's just affine n space. And as many of you will already know, what a unipotent group looks like is this. It's built from the additive group of the field, in this case the complex numbers, by central extensions. And if it has dimension n, that means there's n steps. Okay? So very simple. And we can choose the coordinate functions x1 up to xn sensibly in the light of a chain of subgroups like that. So that if we choose xi, so that for all I, the first I, x1 up to xi, are coordinates for the factor g over gn minus I, then we get a chain of Hopf subalgebras going from the complex numbers through Cx1 as a Hopf subalgebra and so on up to the whole subalgebra. So we get called an iterated Hopf aura extension. In a trivial form, we'll see non-trivial versions later. Trivial because the aura extensions are just join a polynomial, a new polynomial variable. So those are what our starting coordinate rings look like. They're just polynomial rings made into Hopf algebras. Okay, so here's the first theorem about them. Take an n-dimensional unipotent group and a Hopf 2 cocycle, J for G. So there's a black box here, by the way, just to try to anticipate a question. Where do these Hopf 2 cocycles come from? That's a whole separate story, which I don't have time to talk about. But we just take it that we can find some Hopf 2 cocycles. So H is our commutative Hopf algebra. Polynomials in n variables, x1 up to xn. So then we take the twisted version. We can keep the chain of subalgebras, H, H1, and so on up to Hn, such that each one is a polynomial extension of the previous one, but non-commutative in general. So it's written there in the penultimate line. Hi is hi minus 1 with xi adjoined and with a derivative partial I twisting the multiplication. And I'm kind of screwed here because I had intended to put one or two reminders on the board, but boards are verboten, it seems. So I just say, if you haven't seen this notation before, it means that if I take an element R from hi minus 1, and I look at how xi multiplies with R, where xi is the variable in the join, then xir minus xir minus rxi is delta of R, delta I of R. Okay, so that's how these multiplications work, and that's where the non-commutativity comes in. And the theorem also says, although it doesn't say here because it's too unpleasant to write on the board, on the slides, it also says what delta I is in terms of J. So there are formulae for the multiplications. And I'll show you an explicit, the smallest non-trivial example in a moment or two. So, as it says there, this means H is an n-step I-hole iterated Hopf extension of derivation type. Derivation type because a more general Hopf extension, you can have automorphisms messing up the multiplication as well as derivations. But there are no automorphisms here. So here's the simplest non-trivial example, and this is another place where it would be great to have a board, but we can't do that. So you have to mentally think, what is that group? I'll try and help you. It's 4x4 upper triangular matrices, and top row has entries 1, x, v, w. Second row has entries 0, 1, y squared upon 2. Third row, 0, 0, 1, y. Fourth row, 0, 0, 0, 1. Okay? So it's four-dimensional. X, v, w, and y are the variables. As an affine variety, it's four-space. And there's what makes it into a Hopf algebra. Those are the co-product, which you can easily check. I'm sure you all know that straight off the bat. There's a non-trivial Hopf 2 cocycle, which has j of x and v and j inverse of v and x being a half and minus a half for those other two values there, and j0 on all the other generator pairs. And using that, we can calculate the twisted multiplication. And it is non-commutative, but only just. There's one element w which twists and its commutator with x is now y, and its commutator with v is y squared upon 2. So the I-hole looks pretty simple. It is pretty simple. It has one partial derivative there at the end, and the formula on the first display line tells us what the partial derivative, the derivation is. The derivation sends x to y and v to y squared upon 2. Okay. Any questions so far? So, we can play this game with any unipotent group of any dimension. Because the outcome is an I-hole, there's a lot of stuff you get for free once you know that, more or less for free. And this is, some of it is assembled in this corollary here. Let's see. The first three are just kind of standard ring theoretic and homological conditions. The two I want to maybe focus a little bit on today are the last two. Every prime ideal is completely prime. Completely prime just means that the factor is a domain. And if we think of the factor being a domain, that condition applying to all prime ideals, applied to the annihilator of a finite dimensional simple module, which is a maximal ideal whose factor has to be a polynomial ring over the complex, or a matrix ring over the complex numbers. But the size of that matrix ring has to be 1, because it has to be a domain by part 4, which means that the simple module has dimension 1. So there are finite dimensional simple modules for these Hopf algebras. After all, it is a Hopf algebra, so it must have at least the trivial one. In fact, it has more than that. But they're all one-dimensional. And of course, there are going to be other simple modules that are infinite dimensional, but that's another story. So one little slide about structure, and then I'll tell you a bit about the representation theory. So if we've got a cotriangular Hopf algebra like these ones are, we can define a two-sided ideal, which turns out to be a Hopf ideal, called the radical, which is basically the stuff in H which is trivial from the point of view of the R form R. So it's the A's such that R of A comma B is 0 for all B and H. So it's a lemma to see that it's always a Hopf ideal, and it's called a radical. And so if H is a twist of a coordinate ring for an algebraic group G, not necessarily unipotent at this stage, and Rj is the twist by the R form J, then the factor by the radical is the twisted Hopf algebra with a two cocycle J for some factor subgroup T of G, and that T is unique up to conjugation depending on J, and is called the support. And really the J and R are sort of non-degenerate on T, and we can analyze that case separately, and it turns out to be quite important for the general structure. So I'm homing in now on representation theory, and mainly I want to talk about representation theory of finite dimensional simple modules. First topic is that they stratify. There are a bunch of factor algebras which we call J, O, Z, G, J. as G runs through a certain set of elements of G, and every simple module factors through exactly one of these strata. So what are these strata? So we keep this notation from the previous slide, but now G is going to be nilpotent. So T is this support, subgroup of G, unique up to conjugation depending on T. And N is the normalizer of T. So fix an element little g and G and let ZG be the double coset corresponding to little g in capital G. So that's just the set of all x, g, y, where x and y come from T. So it's a closed subgroup, a closed subset, I should say, of a G, and it's irreducible. And the magic is that the defining ideal of that closed subset in O of G stays a two-sided ideal in the twisted algebra, which is very surprising, but it's true. And this is what we call the strata J, O, Z, G, J. And so it's an affine Noetherian domain. And as I said a moment ago, every simple module factors through exactly one of these. So if you think of the trivial case for a moment, where J is just epsilon tensor epsilon, so making no change at all. So our twisted algebra is just O of G. So the support of epsilon tensor epsilon, the biggest subgroup on which J is non-degenerate is just the identity. So T is the identity. The double cosets of T are just the elements of G. And so the strata are just the maximal ideals of O of G. And so you're getting one stratum for every simple module. So this process here of forming strata is clumping the simple modules together into bunches as we make the thing more and more non-commutative. So that's the picture. What about the finite dimensional simples? Well, you might guess from what I just said, you're going to keep a subgroup of G. Remember, O of G itself, the finite dimensional simples for O of G are just all the simples, and they're the group, after all, the max spectrum of the group. And so you get, in the non-commutative case, you get a subgroup. And the subgroup is called gamma here in the theorem, and it's exactly the elements G and G which conjugate J to itself. And I'm out of time, so I'll just put those slides visible and not talk about them. But the take-home point is that this group gamma is always non-trivial. If G is non-trivial, it has dimension at least the size of the derived group of T, the derived factor of T. In general, it's bigger than that. So you keep an infinite number of simples, but fewer than you had to start with. So there are many, many questions about these strata and about these twists in general. And so if you're interested, then please look at the archive paper that Shlomo and I posted last month. Thanks very much.
Thank you very much. Any questions? So maybe I have a question. You concentrated on a triangular case, and you thought about the quasi-triangular. What's changes there?
I haven't thought about it. Neither have Pavel and Shlomo, I don't think. It's Harvard. So And I suppose the point is, why do we concentrate on the triangular case? Because the commutative case is already triangular. And so if you use this machinery, you never escape from triangular. So,
That's what I thought. And also the question about the, you use ORA extension with the derivation, not the skew derivation. And this comes naturally in this setup, right? It's not something, it's not a restriction, but you are enforced.
It happens.
It happens.
Yes. Yeah.
So do you think in the quasi-triangular case you would have, probably would have automorphisms, twisted derivation?
So I think
it's like in the quantum matrices setup.
Exactly. If you start from something which is not commutative but quasi-triangular, then yes, maybe, yeah.
Okay, so there is a question.
Yes, so could you please go to the slide where you twist the group algebra of the Unipotent group? I think it was in chapter 2 or something.
This one or back further?
The previous one.
Previous one.
General one.
That one?
Yes. Yeah. I was wondering where this red partial I is coming from, because this was not needed in the untwisted case, right?
Yeah.
So I was wondering, could you think of the extension in the braided monoidal category with the twisted braiding, and thinking of it in this way, that partial I is not needed?
So the question is if this can be converted into to think about braided tensor categories, so that there is the twisting is involved in braiding, not in the derivation, right?
Right. So it's not needed if you extend in this twisted braided monoidal category.
Yeah, I don't know. I mean, the twist is involved in the braiding here. The braiding doesn't stay the same, so so I'm not sure what you mean, really.
The point is that you don't take the usual commutators, but the twisted ones, and in this way you maybe don't need a partial extension. But
Yeah. Okay, I don't know. There was another question.
Yeah. Please.
Do you have an idea of what would happen if you go from unipotent to solvable?
So the question is whether you have an idea what happens when you go from unipotent to solvable groups.
Yes, I have an idea. We have an idea, but we don't have some partial results. Sure, but there's a step before. There's unipotent, then general nilpotent, because there's no tori here, and that's quite easy. And I haven't bothered to say that, but one has to do that first, and then general solvable. I don't know, and then beyond, of course. Galacki and Ettinghoff looked at semi-simple, but then of course you can combine solvable and semi-simple to get arbitrary. And so yeah, there's a long way to go.
Any other questions? No? So thank you very much. I guess we have a break. On my program doesn't say what kind of break it is. It's a coffee break. Great.
We know where to go.
Sorry?
Where is the coffee?
Alessandro? Right, so our next speaker is Kenichi Shimizu, and he will be talking about quasi-Frobenius algebras in finite tensor categories.
So thank you very much for introduction. And yes, so I have visited sometimes to European country, but actually this is the first time for visiting Italy. And I also thank you for the organizers for giving me to this opportunity to talk here. The title of my talk is Kaji-Frobenius algebras in finite tensor categories. So I first talk about some overview of this talk. So recently tensor categories are applied in many areas of mathematics and mathematical physics. So in some applications, Frobenius algebras play an especially important role for that applications. And because of this, so my first question is, how can we construct Frobenius algebra in tensor categories? Namely, in ring theory, there are so many constructions of Frobenius algebras. So I want to know how can we extend such a construction to the setting of tensor categories. And in some applications of such a Frobenius algebra or tensor categories, actually, in some cases, the category of modules of a Frobenius algebra is rather essential for that application. So we have another natural question. What is a class of algebras that are Morita equivalent to Frobenius algebras? So if we consider the category of vector spaces, more precisely finite dimension vector spaces, then the answer of this question is very well known. Namely, finite dimension algebra is Morita equivalent to a Frobenius algebra if and only if it is a Kaji-Frobenius algebra. So I want to know the answer of this question, and I want to name such a class of algebra as a Kaji-Frobenius algebra. And in a word, this talk is based on my recent preprint, where the notion of Kaji-Frobenius algebra in finite tensor category have been introduced. And I have established some basic theory for Kaji-Frobenius algebra to answer these questions. Okay, so this is an overview of my talk. So I want to now introduce some basic terminology for finite tensor category and related topics to talk about some main results of my talk. So throughout this talk, I will denote by K the base field. I don't assume nothing about this base field. So K may be positive characteristic or K may not be algebraically closed. And by mod A, I denote the category of finite dimension right A modules, where A is some algebra. So now I can introduce the notion of finite abelian category, which is a basic framework for this talk. So finite abelian category is a linear category that is equivalent to mod A for some finite dimension algebra. Actually, there is also an intrinsic definition. Namely, a linear category is a finite abelian category if and only if it is an abelian category. It has only finite many simple objects up to isomorphism, and it has finite dimension homospaces. Every object has finite length, and every object has projective cover. I think that's enough. So I'm sorry if that's not enough. But anyway, so instead of such a complicated definition, so this is an equivalent definition. Namely, finite abelian category is a linear category. That is, namely, mod A for some finite dimension algebra. And this alternative definition is very easy to memorize. So I mainly use this. So now I can introduce the notion of finite tensor category. It is a finite abelian category equipped with a structure of a rigid monoidal category such that the tensor product functor is bilinear and the endomorphism algebra of the unit object is isomorphic to the base field. And given a finite tensor category, one can define the module of a finite tensor category. More precisely, finite left C module category, where C is a finite tensor category, is a finite abelian category equipped with a structure of a left C module category. Namely, it has an action that is right exact in each variable, and associative and unitary up to isomorphism in a similar way as a monoidal category. So actually, such an isomorphism is a part of the structure of a left C module category, but I'm sorry, so for short explanation, I wrote such like this. So anyway, these are basic framework in this talk, and the typical example is this. So mod H for some finite dimension Kaji-Hopf algebra is an example of finite tensor category. And given such a category, we can construct a finite left C module category from a left H comodule algebra. So namely, mod R for some finite dimension left H comodule algebra R is actually an example of a finite left C module category. Okay, so I continue to introduce more terminology, which mainly came from ring and module theory. Okay, so let C be a finite tensor category and let M be a finite left C module category. And an important notion is the internal Hopf functor. Namely, we can define underlying Hopf by using such an adjunction. So once we can prove that such an object exists, then we can show that it is unique up to isomorphism by the Unipotent lemma. And actually, by the finiteness and some related assumption, we can show that internal Hopf functor exists for finite left C module category. And by using this assumption, we can define the so-called composition morphism between the internal Hopf functor. So namely, if we have, okay, so in an ordinary setting, if we have a morphism from X to Y and a morphism from Y to Z, then by composing them, we can get a morphism from X to Z. And such an analog of such a operation can be defined for the internal Hopf functor by using this adjunction. Okay, so now by using the internal Hopf functor, we introduce some basic terminology which is closely related to the same named notion in the module theory. Namely, we say that an object of a finite module category is, say, C projective if this functor is exact. Namely, this is completely an analog of the notion of projective object in the category. And similarly, we define an object M to be C injective if this functor is exact. And similarly, we define an object object M is C generator if this functor is faithful. So these are completely an analog of the same name notion in the ring and module theory. You can find some useful properties of these notions in this paper. Okay, so now I continue some basic properties of a C projective object. So first of all, there is such an isomorphism. And by utilizing such a natural isomorphism, we can show that, we can show this lemma. Given an object M in the finite module category, we see that M is C projective if and only if P tensor M is projective for any projective object in C. And if and only if there is a non-zero object such that X tensor M is a projective object. And a similar result holds for C injectivity. So we have some useful consequences. So for example, every projective and injective object of M is C projective and C injective, respectively. So in a sense, C projective objects are generalization of the notion of projective object in an ordinary sense. And the C injective objects are generalization of injective object in an ordinary sense. And we also have, so Ettinghoff and Ostrich introduced the notion of exact left C module category as a finite left C module category, satisfying for every object of M, this condition is satisfied. So we can rephrase their definition as follows. An exact left C module category in the sense of Ettinghoff and Ostrich is the same thing as a finite left C module category where every object is C project. So in a sense, exact left C module category is a kind of C semi-simple category. C semi-simple category. Okay, so I have already introduced some basic terminology. So I shall explain some basic results in Morita theory in finite tensor category. So maybe I can skip this slide, but an algebra in C is an object A together with some morphisms, which is called the multiplication and unit, satisfying certain associativity and the unit axioms. And given algebra A, modules are defined in a similar way as the ordinary case. So I introduce this notation. Let CA to be the category of right A module in C. And then one can show that this CA is actually a finite left C module category. And by using this notion, we can, we can consider some Morita equivalence and Morita theorem for these algebras in the finite tensor category. So namely, given two algebras A and B in C, they are Morita, we say that they are Morita equivalent if CA and CB, which are left C module category, so two algebras A and B in C are Morita equivalent if CA and CB are equivalent as linear left C module categories. And one can characterize this Morita equivalence by using Morita type theorem. namely if P is an C projective C generator, then this functor is actually an equivalence. Actually, these results are special case of some very general results given by Paredes in this paper. So, namely, both Paredes established some results on such a C module category and Morita equivalence in algebras in monoidal categories. And actually, these results are just a special case of some known results, which go back to 1978. Okay, I think I have introduced almost main players of this talk. But I'm sorry, so I forget to introduce one of main very important player in this talk. So, okay, so in this talk, I call an algebra A Frobenius if A and A dual are isomorphic as right A modules, where A dual is built as a right A module by this action. And in this talk, actually being Frobenius is a property for an algebra, unlike the talk of Stefan. Namely, sometimes Frobenius algebras are defined to be an algebra equipped with some additional morphisms. And usually, sometimes we require a morphism of Frobenius algebra to be to preserve such additional structures. However, in this talk, I use this term as a property of an algebra. So there may be a non-isomorphic, how to say? Okay, so there are non-isomorphic morphism of Frobenius algebra because of this assumption. So, as I have mentioned at the beginning of this talk, Frobenius algebra played a very important role in some applications of tensor categories. So, for example, in subfactor theory, so an extension of factors can be can be encoded in the so-called Q system, which is Frobenius algebra satisfying some properties. And also a similar result is known in conformal field theory. Namely, under some nice assumptions, an extension of vertex operator algebras can be described by a certain class of algebras, which may be Frobenius. And in topological field theory, so especially in two-dimensional topological field theory, there is a one-to-one correspondence between Frobenius algebras and two-dimensional TQFT. So in this sense, Frobenius algebras are very important for some applications of tensor categories. But sometimes the category of modules of a Frobenius algebra is rather essential than the algebra itself. Or it is important to know what is property of modules of a Frobenius algebra to construct some new class of Frobenius algebra. So now I can pose some natural questions, which I already introduced at the beginning of this talk. So how can we construct Frobenius algebra in finite tensor categories? And what is a class of algebras in finite tensor categories that are Morita equivalent to Frobenius algebras? Okay, so I'm going to answer these questions by introducing the notion of Kaji-Frobenius algebras. And actually the definition is not so difficult. We say that an algebra A in C is Kaji-Frobenius, which is written QF for short, if A in the category of right A modules is C injective. So please recall that CA has a structure of a finite left C module category. So we can define the notion of C injective object in the category CA. So we say that an algebra A in C is Kaji-Frobenius if A is C injective. And one might prefer to call this self-C injective algebra in C. But anyway, so I decided to call this Kaji-Frobenius algebra. So I want to introduce some examples. So first of all, every Frobenius algebra is a Kaji-Frobenius. Namely, Frobenius algebras are a proper generalization of the notion of Kaji-Frobenius algebra. Because, so indeed one can prove that A dual in CA is always C injective. So this is an analog of the fact that A dual is injective for, how to say, this is a anyway, so this is an analog of the well-known fact for finite dimensional algebra. We can prove the same for any algebra in a finite tensor category. And if A is a Frobenius algebra, then A dual is isomorphic to A by definition, and therefore A is also C-injective. So this is a proof of this proposition. Every Frobenius algebra is Kaji-Frobenius. And now I introduce another class of Kaji-Frobenius algebra. So every Hopf algebra in a braided finite tensor category is, in fact, Kaji-Frobenius. So it may be, I'm not sure it's well known, but for some Hopf algebra in a braided finite tensor category is not necessarily Frobenius algebra. But actually they are Kaji-Frobenius algebra. Okay, so the proof is as follows. Let H be a Hopf algebra in a braided finite tensor category. Then according to the fundamental theorem for Hopf modules, there is an invertible object, which I write int H, such that there is an isomorphism of Hopf modules. And the claim can be verified by using this in a similar way as this proposition. And actually, so take, for example, C to be the category of super vector spaces with supersymmetry, and take H to be the exterior algebra of our odd vector space. Then we see that H is not Frobenius algebra if the vector space has odd dimension. I'm sorry. So here odd means the dimension as a vector space is odd. But anyway, so there is such an example. So a Hopf algebra in a braided finite tensor category is not always Frobenius, but always Kaji-Frobenius. So now we can know that this class of algebra is very broad class of algebras. Okay. So now I want to give a characterization of this class of algebras, such like A is. So actually, we will show that an algebra A in C is Kaji-Frobenius if and only if it is Morita equivalent to a Frobenius algebra. So to show this, I need to introduce some related notions. So first important tool is the so-called Nakayama functor. So for finite dimension algebra, the Nakayama functor is defined by this formula, namely just by tensoring A dual over A. And so I introduce this notation. So proj A is a category of projective object of the category mod A, and inj A is a category of injective object of the category mod A. So from the theory of rings and modules, we know these facts. First of all, there is a natural isomorphism between this home space and this home space. And the functor NA actually induces an equivalence between the category of projective objects to the category of injective objects. And it is known that the algebra A is Kaji-Frobenius, of course in the category of vector spaces, if and only if NA, this functor, is an equivalence. And so actually, recently, this notion has been extended to finite abelian category. Namely, finite abelian category is equivalent to mod A for some finite dimensional algebra A. So we can define the same named functor by using such an equivalence. But actually, the resulting functor is doesn't depend on the choice of such an equivalence. So we can define for finite abelian category the Nakayama functor without differencing algebra A such that M is equivalent to mod A. So you can construct this important result to the paper of Fuchs and Sherman and Schubert. Okay, so now I introduce the second important tool for the Kaji-Frobenius algebra, which I call the relative cell functor. So given a finite finite left C-mod category, I denote by PCM the category of C projective objects, and ICM to the category of C injective objects. And we can define the relative cell functor as follows. It is a right exact end functor, specifically right exact linear end functor on M, satisfying this condition. Namely, hom PM star is isomorphic to hom M SMP. So this is completely analog to the case of Nakayama functor. So namely, by generalizing this property of the Nakayama functor, I introduce the relative cell functor. And actually, Fuchs, Sherman, and Schubert considered the same notion in the case where M is an exact left C-mod category, which is equivalent to the case where PCM is equivalent to PCM is equal to the full category M. So actually, this is a slight generalization of their notion of the relative self functor. So I introduced some proposition related to internal Hopf functor and relative self functor for the case where M is a category of some modules over algebra in C. Namely, if M is equal to CA for some algebra A in C, then the internal Hopf functor is given by this way. And by using this description, we can show that the relative self functor is isomorphic to this object. So because we are considering the general finite tensor category, actually M double dual may not be isomorphic to M no more. So we cannot drop this double dual functor in general. And so the right A module A star is actually this is slightly tricky, but A dual is actually built as an A double star A bimodule by this kind of action. So by using these tools, we can now, I'm sorry, so before that, I need to explain some basic results for relative self functor. So this is the basic properties of the relative self functor given in my preprint. So first, the relative self functor exists and is unique up to isomorphism. And there is and the relative self functor induces an equivalence from PCM to ICM, like the case of the Nakayama functor. And actually, the Nakayama functor and relative self functor has a close relation. Namely, SM, relative self functor, is isomorphic to Nakayama functor plus the action of this object, where alpha is defined by NC1 dual. So when C is a category of modules over finite dimensional Hopf algebra, actually this alpha corresponds to the so-called distinguished group-like element, or sometimes called the modular function on that Hopf algebra. Anyway, so relative self functor and Nakayama functor, in general, they are not isomorphic, but actually the difference can be written in terms of the modular function on the finite dimensional Hopf algebra. Okay, by using such a result, we can give a certain construction of Frobenius algebra. Namely, if P is a C project such that P is isomorphic to the SM of P, then this algebra is a Frobenius algebra with this isomorphism. Namely, A dual is, by definition, isomorphic to Hopf PP dual. Here, internal underlying Hopf is the internal Hopf functor. And by the defining formula of the relative self functor, this is isomorphic to Hopf P SMP. But by assumption, SMP is isomorphic to P, so this is isomorphic to Hopf PP, which is equal to A. And we can show that this resulting isomorphism is actually an isomorphism right A module. So we can show that this is Frobenius algebra. And actually, this is one of main construction for this talk. Okay, so now I give some consequences. If a finite depth C module category M has a C projective C generator P such that P is isomorphic to SMP, then A is a Frobenius algebra by this theorem. And by Morita theory, M is equivalent to CA. So we can give a sufficient condition for a finite depth C module category to be the category of modules of a Frobenius algebra. And the assumption is satisfied. For example, SM is an equivalence. So, for example, take P to be the direct sum of P1 to Pn, where Pi's are representative of isomorphism classes of indecomposable projective objects. You can easily show that this object is fixed by any autoequivalence. So, if we assume that SM is an equivalence, then we can show that M is actually a category of modules of a Frobenius algebra. And actually, this is one of characterization of the notion of Kaji-Frobenius algebra. Okay, so this is my main theorem. So techniques of Nakayama and relative self functor yield these conditions are equivalent for algebra A. So first condition is A is Kaji-Frobenius. Please remember that this is defined to be an algebra A such that it is a C injective as a right A module. And that is equivalent to that A dual is C projective. And so this is a similar characterization for Frobenius algebra. Namely, every C projective object of CA is C injective. and every C injective object of CA is C project. This is equivalent. And the relative cell functor of CA is an equivalence, and the Nakayama functor of CA is an equivalence. And the algebra A is Morita equivalent to a Frobenius algebra in C. And actually, in the condition 7, the condition 7 is somehow left and right symmetric. Once we can prove that 1 to 7 are equivalent, then we can also show that left module version of these conditions also equivalent to the condition that A is Kaji-Frobenius algebra. So I skipped the detail of the proof, but anyway, so we prove these by using the Nakayama functor and relative cell functor. Okay, so I introduced some variants of this notion. So asymmetric Frobenius algebras are important class of Frobenius algebra, and we can define the same name notion in any finite tensor category equipped with a pivotal structure. Namely, okay, so we now suppose that the finite tensor category C is pivotal with pivotal structure Px. And a symmetric Frobenius algebra in C is an algebra A in C such that A dual is isomorphic to A as A bimodules, where A dual is viewed as an A bimodule by the pivotal structure. So please remember that A dual can be regarded as A double dual A bimodule. But now, under our assumption, A double dual is isomorphic to A. So by identifying A double dual with A, we can view A dual as A bimodules. And if this A bimodule is isomorphic to A as A bimodules, then we say that A is symmetric Frobenius algebra. So this is a kind of natural generalization of the notion of symmetric Frobenius algebra in an ordinary sense. And natural question again arises. What is the class of algebras in C that are Morita equivalent to symmetric Frobenius algebra? So if we drop the symmetry C assumption, then the answer of this question is Kaji-Frobenius algebra. So we want to know a symmetric version of this question. Okay, so to answer this question, we consider an algebra, an extension of this pivotal structure to a module category and by introducing a notion of pivotal module category. So actually relative cell functor plays a kind of role of double dual functor. So if relative cell functor is isomorphic to the identity, then we say that the finite left C module category is pivotal. So actually the technical, so there are some technical difficulty, but naively, relative cell functor plays a role of the double dual functor. So we introduce a pivotal module category to be a module category whose relative cell functor is isomorphic to the identity. So this is a formal definition, and actually we can show this theorem. So if M is a finite left C module category equipped with a pivotal structure, then for every projective C projective object in the category, then its internal endomorphism algebra is a symmetric Frobenius. And for an algebra A in C, the following are equivalent. A is symmetric Frobenius if and only if CA has a pivotal structure. And because of this, namely, the second question is complete with a property of the category of modules. So we can show that the class of symmetric Frobenius algebras in C is closed under Morita equivalence. So namely, okay, so the class of algebras in C that were Morita equivalent to symmetric Frobenius algebras are symmetric Frobenius algebras. Okay, so this is kind of easy examples, but because I have no time, so I recall the summary of this talk. So I have introduced the relative cell functor for finite left C module category and established its fundamental properties. And by using this, I introduced a notion of Kaji-Frobenius algebras and its Morita theoretic characterization. And also as a bonus, I have some characterization of the class of symmetric Frobenius algebras. So thank you for listening.
Thank you very much. Any questions? Please, Sebastian.
Hi. So for usual quasi-Frobenius algebras, they are connected with the notion of reflexive modules. That a finitely generated module over a quasi-Frobenius algebra is indeed reflexive. Do you know whether the same result holds in your setting?
So you mean, so, I'm sorry, so please, what is the question?
The question is, if I have a quasi-Frobenius, a normal quasi-Frobenius algebra, then a finitely generated module over that algebra is reflexive. Is the same true in your setting?
So the answer is, I'm sorry, I don't know. So how to say? So in my setting, I always work in a finite tensor category, where every object is finite length. So I implicitly assume everything to be finite. So because of this, I didn't consider what you asked. So maybe because of this, I have no answer. Thank you very much for question.
Are there any other questions? I don't see any, so thank you very much again. And the next talk starts in a couple of minutes. Right, so our final talk this morning session is given by Fosco Loredian on the fibration of algebras. Over to you, Fosco.
Thank you. So let me start joining in thanking the organizers. I'm very happy to be here. Unfortunately, I have to leave today, this evening. So I hope you will have questions for me and we can discuss this story a little bit, but I only have today. So, as you can see, this is a joint work with a bunch of people. Daniel Aman and Ulo Reima are from University of Tartu in Estonia. I'm from Tallinn, they're from Tartu. There's only 2 universities in Estonia. Greta Coraglia and Davide Castelnuovo are old friends from many years. They basically work in, they're both in Italy, they're both Italians. They basically work in categorical logic, type theory. And Nelson Martins Ferreira is in Leiria, in Portugal. He works in categorical algebra, representation theory, especially representing actions of monoids. So you see a pretty diverse bunch of people in a big group, many experiences come. And in fact, I'm pretty happy to present this work at this conference because Hopf algebras became an example, a motivating example among many others. So I hope that this language can unify and provide ideas from outside of algebras and monoidal categories that come from, for example, from logic, because there is a unifying concept behind some constructions. If you want to know more, a small part of my story is a small part of a paper that appeared on Archive 3 days ago, so you can go there and have a look. So, a little plan of the talk. I will start telling you what I mean by a fibration of algebras. It's something that probably, if you have seen me giving talks, I have been working with this for a little while already, but I want to fix the notation, the nomenclature a little bit, and then I will mention the motivating example among many others, which is a very famous, a very deep theorem that is about reconstructing Hopf algebras from pieces. Then I will dive into a fairly formal, but in my opinion exciting aspect of this story, which is the possibility to use the language of these fibrations of algebras to provide a motivating, a quite compelling example of what is an exact sequence of categories. And then when you have an extension problem, then probably you have a cohomology. I will not go that far, but I think it's a pretty neat way to formalize, to conceptualize the ideas. And then I will describe some more structural results, a bit diverse. I will keep this example if you want to wrap your head around the definitions, the abstract definitions. I made sure that the examples are, that this is an example of the definition I will give. So it would really be a motivating example. So the definition, the basic object that I want to study here is a fairly simple kind of gadget. It's a functor defined from A times X, A and X are two categories, into X. And I will call this a parametric endofunctor for the obvious reason that I can think of A as a category of parameters and X as a category of carriers for every endofunctor of X that is obtained by fixing an object in A. Anytime I need to use this form of F instead of this, by evident reasons they are interchangeable, and this makes clear why I want to think of these as parametric endofunctors, because if A is a point, this is just an endofunctor. If A has more objects and morphisms, I'm specifying a family of endofunctors of X in a compatible way with the structure of A. So, to each of these endofunctors, one can associate fairly naturally several objects. For example, if Fa is a mere endofunctor, it doesn't have any additional structure on it, you can just consider the category of Fa algebras, endofunctor algebras, or Fa coalgebras, dualizing. But if Fa is a monad, maybe you're interested in looking at the categories of Eilenberg-Moore algebras, because you want to keep track of the fact that Fa is a monad. And dually, if Hfa is a comonad, you can consider the co-Eilenberg-Moore algebras. You can also consider Kleisli and co-Kleisli categories, respectively, if Fa is a monad or a comonad. You can. It is a little bit subtle how to make Kleisli and co-Kleisli fit into the picture. I will basically almost always talk about monads and these categories here, Eilenberg-Moore of Fa. Let it be sufficient that you can work with this. It's a little bit more subtle. If one specific example will require, I will explain better. So each of these associations defines, for evident reasons, a pseudo-functor, because each of these is a category depending on A, which can be covariant, contravariant, depending on what is the variance of the construction that associates algebras or coalgebras to F. And well, whenever you have a pseudo-functor of this type, you can obtain a category fibered over A. So, because there is a certain construction that in recent times it's been called straightening and unstraightening, the two inverse operations that provide the pseudo-functor from the fibered category and vice versa. But I prefer to call it the Grothendieck construction, or actually the Grothendieck-Benabou construction, because it was initially discovered in the most general form by Jean Benabou, but that's just nomenclature. What I'm interested in is using the fact that I obtain a fiber category over A, which is a fibration in cases where the association of this functor is contravariant, or an Hopf fibration in the cases where it's covariant. Not only this, it's a split fibration, it's a specific, well-behaved kind of fibration. It doesn't really matter, it's a technical condition that makes coherence diagrams work a little bit better. I will not dive into any proof, but if you know what is a fibration, very good. If you don't, a fibration is essentially a functor with codomain A from some domain that has a very nice property in terms of the structure of A inducing some, the presence of a morphism in the base, inducing providing some information for the structure of the fibers, meaning the objects that map to a single given A in the base. So, when I have these fibrations, of course I want to study them, I want to classify them, and of course I can keep track of where they come from. Here I specified a functor which is just an endofunctor, and I consider every fiber here is the category of endofunctor algebras. Here I do the exactly dual thing. Here I consider the Eilenberg-Moore categories of what I call a parametric monad. Here I do it for comonads, and here I take the Kleisli categories. The notation is pretty self-explanatory. I want to find examples, because if I don't find examples, this theory is for nothing. And when I have examples and I have some fairly evocative notation, I want to develop a general theory. I want to prove theorems that maybe explain a little bit better and conceptualize things that people have been doing, finding in a seemingly disparate bunch of parts of mathematics, category theory, algebra. So the motivating examples that we found have to do with a little bit with all of these things. Representation theory, of course, gives many examples, but also there are examples, and a fairly strong motivating example comes from type theory and categorical logic, because these fibrate categories are the main tool to do categorical logic. There is a certain interest, especially in people trying to apply category theory to computer science, to a generalization of monads that are called graded monads. There are examples there. Another fairly large class of examples come from the theory of coalgebras and from automata theory, formal languages, etc., which is between logic, computer science. So you see a pretty diverse bunch of areas of mathematics where you can find examples of these constructions. The moral is, whenever you have a functor of this type, and it's fairly common to have a parametric endofunctor, plus maybe additional structure, you can construct these things, and then I hope some of these structural theorems help you to classify, to understand what is the property, what are the properties of the endofunctor regarded as, so to speak. Here you're considering not only the algebras or the Allen-Bemur algebras for a single object, but you're considering global properties, and you're also considering how the properties of FA vary if you change the object, and you have a domain, the domain of the fibration, where these can be taken into account, where if you have a morphism in the base, then you must have a functor between algebras here and algebras there. So, Hopf algebras provide this, the theory of Hopf algebras provided us with this theorem. It's a fairly famous result. If you have a cocommutative Hopf algebra over a field that is algebraically closed and characteristic 0, I hope I didn't forget any assumption, then you can present H as some sort of semi-direct product. You can decompose it in a certain sense as a group, or rather the group algebra over that group and the Lie algebra over the same field. And this fact that the object of a category can be presented as a semi-direct product is also, like, I sneak this notation onto you because I consider the domain of these fibrations with a notation that says that the domain of these categories is some sort of semi-direct product of A and X.
Is it always A here at the bottom of the slide, or is it X?
Yes, it's always A, yes. So the idea that you have to keep in mind is that whenever you have a functor like this, you're essentially saying that A is acting on X, because this has exactly the type.
There's an X in the codomain.
Yes.
And you have A in the codomain.
This is X?
Yeah.
A times X into X.
But on the next slide, no.
And then? Yes?
No? One.
More?
Yeah, no.
Yeah. Yes, because this construction takes a pseudo-functor from A and gives back a fibration over A. It turns stuff that maps out of A into stuff that maps into A. That's why it's a subtle, it's a powerful construction, because in principle you don't expect to have a way to transform this pseudo-functor into something that goes into A, but you can. And Grothendieck told us, and Benabou told us how. So the thing is, A is acting on X through the representation, if you want, given by the parametric endofunctor. It's a fairly natural idea. And if you follow this idea, if you bear with the idea, then I think I can make a point that yes, oh, this is a typo, yes, this should be X, sorry. I think I can make a point, besides the typo, that yes, this object behaves like a semi-direct product. So, a first hint of this is that the fact that you can decompose Hopf algebras over K as a semi-direct, every object, as a semi-direct product, is a consequence of the fact that this category can be presented in this form as the Eilenberg-Moore fibration of a parametric functor, where A is the category of groups, X is the category of Lie algebras, and then the functor essentially sends G, or rather KG, to the category of Lie algebras equipped with an action of KG under Lie algebra homomorphisms. So if you unwrap this, the fact that you can present CCO of K as this essentially is equivalent to this theorem. One is true even only if the other, and when you prove that you have this decomposition, of course you have to invoke the theorem. So my intuition over this result is that this is true, every object is decomposable because the category is decomposable, so it doesn't happen by chance. Now, let's try to keep in mind that whenever I state a general theorem, because now I will state a general theorem, you can have this example in mind, where A is the category of groups, X is Lie algebras, and the central object is Hopf algebras. And now, bear with me, because I will consider a parametric monad, so every TA is a monad, and every morphism in A induces an homomorphism of monads, so compatible with the monad structure on the different parameters. And then you can definitely send any object here to an object in A that is given by the projection, by the fibration map. But you can also take an object here, which is a triple, parameter, carrier, and algebra structure. You can forget everything but the carrier and just keep the carrier of the algebra structure. This gives you a functor that has the very nice property to create limits. So you can, actually, limits here are, if you try to understand how to compute a limit of a diagram here, starting from the fact that A and X admit limits of the same shape, it's very easy to notice that it's easy to compute these limits because you just project them down, you compute the limit there, and this limit inherits naturally a structure of an algebra. So this happens because this pair functor, PV, into the product creates limits, and in fact it does because it's monadic. So if I have a parametric monad, then well, I can construct in a fairly easy way a monad, a single monad, on the product category that of course is equivalent to the initial parametric monad because it will act, T hat will act as sending AX to A TA of X. So in particular, this monad will be fibered over the projection, over the trivial fibration. And giving you T hat and giving you T is essentially the same thing. But whenever I give you T hat, I give you the canonical factorization into free and forgetful. And this is exactly, PV is exactly the forgetful of T hat. So if this notion reduces to just a monad on the product, why go all the way to understand parametric monad, parametric endofunctors? Why change the setting? Well, because if you keep working with the functors P and V separately, so if you start from the parametric functor and you construct all the data, and with very minimal assumptions, see that X has a terminal object and A has an initial object, you can draw P and V, and I sneakily drew them in this way because you can easily see that the functor V that forgets everything but keeps the carrier of the algebra has a left adjoint given by the free algebra, but over for what monad? Well, for T at the parameter initial object of A, and see I'm using this second property, and in a similar fashion, P, the projection, has a right adjoint that picks the terminal object fiber-wise. Very simple construction, where I use this other minimal assumption that X as a terminal object. This is nice, because then, if A and X are pointed categories, they admit a zero object, well, I can write an exact sequence of left adjoints, where each of these functors is a left adjoint, that it's exactly saying that, in a certain sense, to be precise, the central element is an extension of this by that. So, how far can you go if you follow this idea, this exciting idea? Well, you can define a two category of sequences where you extend A by X, and the central element is some other category. P is a fibration, and each of these functors is a left adjoint. So you can have you can take the P and the left adjoint Y to get a functor into X times A, and you can recognize inside this two category by purely two categorical ways which objects are of the form a fibration of algebras, because you know that P comma V into the product has to be monadic. It's an if and all if. So the arrows from E to the sequences of this type that generate a functor into the product, which is monadic, they must correspond by essentially just two-dimensional and waving to categories of the form. They must come from a parametric monad. There is a subcategory inside this, which is spanned by those sequences where Pi is constant at the zero object, and this is the analog of an X1 group, so to speak. And again, in homological algebra 101, you prove that this is if A and X are modulus over a ring, this is a module of the same ring. Here you can prove that with minimal assumptions, A and X has to be pointed categories, then taking the product of sequences gives X1AX a monoidal structure, symmetric monoidal structure, which is nice. I don't want to go into the technicalities, but I think this is a hint that this is something. There's another result then that has to do with Hopf algebras. It's a very recent paper by Marino Gran, Cajo, and Joost Verquist, where they construct a torsion theory on the same category as before, but now we know that the category can be decomposed as a semi-direct product. So if you know what's a fibration of Eilenberg-Moore algebras, you wonder, well, maybe I can do this in general. So the comfortable assumption to make everything work is that your category has to be semi-abelian, but if you take them semi-abelian and you equip them each with a torsion theory, which you can present them a torsion theory as a pair of subcategories subject to conditions, or with a certain well-behaved factorization system, but it doesn't matter. I prefer to work with factorization, but it doesn't really matter. They are equivalent languages. So then if you take a suitable kind of parametric monad, then you can essentially lift the torsion theory on the two pieces, on A and X, separately. You can take, in a certain sense, evident sense, the semi-direct product of the two torsion theories, and you get a torsion theory on the total category. And it's basically just an elaborate observation of the fact that if I give you two ways to factor morphisms in A and in X separately, then whenever the monad satisfies some mild assumptions, I can factor an object in the total category, in the Eilenberg-Moore fibration, exactly as I would like to be able to. Because, well, I didn't introduce this notation, but this is exactly to say that the object is a parameter, a carrier, and psi is an algebra structure, and same for B, Y, and theta. So a morphism is something from X to Y and something from A to B, F from X to Y and U from A to B. And then what do? I factor U and F with respect to the two factorizations, and this works. Very nice. And recovers the theorem as a particular case, puts the theorem in a more conceptual, more general framework. Another result that I find interesting is the fact that, well, this is a fairly well-known fact in basic algebraic topology. Whenever I give you a fibration of spaces, what happens is that every fiber over a point has a certain natural way for which the fundamental group of the base can act. So now we have fibrations of categories, and I want to convince you that there is a theorem that behaves in a similar way. Now, if I give you a fibration, P from E to A, not of Eilenberg-Moore from a parametric monad, doesn't come from that, but I can build, in a certain canonical way, a parametric monad out of, and so a fibration of Eilenberg-Moore algebras out of P, with, again, not so strong assumptions. P has to have a fully faithful left adjoint, and then some coproducts of the form the initial object in a certain fiber plus something in the fiber over the initial object. They have to exist. But don't worry about this. It's a technical, not very enlightening condition. But with these assumptions, I can build a parametric monad out of P, which essentially says that now the base of the fibration is acting over the fiber of the, or on the initial object via monads. And then whenever I have these, I can build another fibration, the Eilenberg-Moore algebra fibration of TP, and then I can compare P with the fibration of Eilenberg-Moore algebras obtained from TP, and this turns out to be a reflection, which is a surprising result, because you wouldn't think that given any fibration with reasonably mild assumptions, there is a way to build a parametric monad out of it, and then this fibration compares with the one obtained from the monad. But not only this, the subcategory of parametric monads with the very surprisingly mild condition that TP at the initial object must be the identity, they are a full subcategory under the construction that builds the Eilenberg-Moore fibration of a subcategory of certain well-behaved fibrations. This is, I was quite surprised, because you have this theorem in algebraic topology that says something that has a long, renowned history, and you wouldn't expect that something similar is true for our fibrations, but not only it's true, but it elucidates the fact that parametric monads, when they are reasonable, they are exactly described by their fibration of Eilenberg-Moore algebras, which is nice. So, let me wrap up. I don't know how much time indeed I take, but let me wrap up. We have more examples. I focused on the Hopf algebra examples to motivate the need for a general theory, but examples come from other parts of representation theory, from algebraic geometry, from categorical logic type theory, the uses of category theory in co-induction in computer science. And again, the moral is that whenever you have an endofunctor that depends on a parameter, there you have an example of a fibration of algebras in some sense. You can push further the story of the categorified extension groups. Perhaps you can even talk about higher extension groups. I didn't go that far, but because there's already a bunch of things that you would like to understand about X1 and how the extensions of degree 1 behave. There are nice consequences of monadicity that I don't want to explore here, but that essentially make the total category of the fibration of Eilenberg-Moore algebras some sort of rigid object whose structure is specified by how you do formal theory of monads in the sense of street in the two category of fibrations over A. This is also something interesting that probably makes some arguments in the paper even more streamlined. You can push this quite far by using this monadicity idea in a fairly more general setting, but this is for a moment much more in the future. You see, it's a long-term project. There's many people involved, and each of them is giving something for this such a variety of applications, such a variety of examples. And I hope you can also find something interesting in this. Let me know. And I'm open to questions and to discussion. I'm done.
Thank you very much. Any questions?
Many questions.
Good. Yes, please.
Thank you for the nice talk. So my question is a bit like this. So your functors from A product X to A, to me, look a little bit like cleaving maps. So I was thinking if cleaving maps, or let's say smash product algebras or cross product algebras, somehow enter your theory.
So the functor, you mean in the very beginning, the parameter? Yes. Okay. And you said which algebras?
Cleaving maps or smash product algebras?
I'm not familiar with this notion, with this definition, so I have no idea, but
Maybe we can talk later.
yes, absolutely. Thank you.
Thanks a lot. More curiosity. There exists an analog of the categorical constant theorem for groupoids and the algebroids developed by Kalischnik, if I pronounce the names correctly. Did you already try to see whether you can describe also something similar, so something at the OID level with your machinery, and if it becomes clearer what is going on?
No, we haven't, and I think I'm doubly guilty because you already asked me this question in Louvain, and I was ashamed, and I was ashamed that we didn't already. To be honest, I provided the two category theory. You have to talk with Ulo or with Nelson for the representation theory aspects. But yes, I think it's a very reasonable question. I just don't know yet. Thank you.
Any other questions? I don't see any. So thank you very much for your talk, and thank you to all the speakers of this morning. It's time for well-deserved lunch break.
Okay, welcome back. So we are going to start the afternoon session. So our first speaker is Nguyen Thi Hoa from the University of Clermont-Ferrand,
Yes.
Who will speak about cohomological dimensions of braided Hopf algebras.
Okay, so thank you for introduction, and thanks to the organizers for our conference. So I have to say that this is my first time giving a talk in front of many people, many famous people in our field. So I'm a little bit nervous right now. But I am also excited to be here today to talk about one of the results I have been doing this year with my PhD supervisor, Prof. Julien Bichon. And so as we heard, the talk is about cohomological dimension of braided Hopf algebra. So to explain our motivation for this work, I'm going to begin with some recall about cohomological dimension. So, thank you. So first of all, let A be an algebra and let M be a Lefty model. We have the projective dimension of M is the smallest possible length for a projective resolution of M, and it can be characterized as the subprime of the set of natural numbers D, for which we have a name model N, such that the X space in the degree D of Mn is not 0. We also have the Hopf cohomological dimension, or simply we say the cohomological dimension is the projective dimension of A as an AB model. And the left global dimension of A is the supremum of projective dimensions of A model, a left A model. And we also have the right global dimension, which is defined in the same way. And when we have the left and right global dimension equal, we just say the global dimension. And we always have the global dimension is less than the cohomological dimension. This is well known. And so we know that the global dimension is an important homological invariant of an algebra, but there's some case it doesn't match with its geometric intuition. For example, the first Weyl algebra denoted by A1, we know that this is a deformation of a polynomial algebra, so we expect that its dimension is 2. However, we know that in characteristic 0, the global dimension of A1 is 1, while the cohomological dimension of A1 is 2. So we should consider the cohomological dimension instead. And a natural question for us is that when do we have the cohomological dimension equal the global dimension? And we know of two important cases when we have where these two dimensions coincide. The first case is when A is a braided connected algebra, and the second case when A is a Hopf algebra. And so we would like to generalize the case of Hopf algebra to braided Hopf algebra. So in this presentation, I would like to outline a strategy to prove our main theorem with my supervisor, Prof. When A is a Hopf algebra in a braided category of co-model over co-quasi-triangular, co-semi-sample Hopf algebra, we have the cohomological dimension equal the left and right global dimension, and these are equal to the projective dimension of trivial left and right model. So to do it, I am going by recalling some concept of braided category. So we have a braided category is a monoidal category, endowed with a braiding usually denoted by a small c, and which is a natural isomorphism. Which means it satisfies some commutative diagrams. And we usually use some diagrammatic notation for the morphism in our category C, or the braiding C and this inverse C minus 1. And the simplest example of a braided category is the category of K-vector spaces with the braiding given by the flip operators. And the second example of a braided category is a category we want to work with. So first of all, recall that a co-quasi-triangular Hopf algebra is a Hopf algebra H equipped with a convolution invertible linear form R, which satisfies some conditions. And then we know that the category of H commodal MH is braided, and with the braiding given by this formula. And so in this scenario, we can consider a concrete example, is that if we have a gamma an abelian group, then we know that the group algebra K gamma is a Hopf algebra, and moreover, it's a co-quasi-triangular Hopf algebra with the braiding corresponds to the pi characters of gamma, denoted by psi. And this is well known that the category of K gamma commotors is identifies with the category of gamma braided vector space. And then with this fact in hand, and given a pi character psi, we know that our category K gamma commotors is braided with the braiding given as the above formula. So now, as we saw, as we have seen, there's also the definition of algebras and co-algebra in a monoidal category with some with the relation as in the usual sense, and we usually use some diagrammatic notation for our structural, and we remark that the structural morphism in our category to being an algebra or a co-algebra in our category. But there's no natural way to formulate a definition of B algebra in a normal category. But this becomes possible in presence of a braiding. Why? Because if we consider two algebra A and B in our category, our braided category C, and the braiding of C gives the object A tensor B a multiplication I describe here, that we just use the braiding to twist B and A in the middle, and then we use the product of A and B to both sides. So this actually gives A tensor B an algebra structure. So thanks to this construction, we can have the definition of B algebra. And then Hopf algebra in a braided category as in the ordinary case. So now to prove our main theorem, we need some construction that we will see right now. The first one is that we always take our braided category is C, and let A be an B algebra in C, and let V be a left A motor in our category. And we can endow V tensor A with the right A model structure divided by the multiplication, by right multiplication. Then the morphism that we have found here, denoted by mu, provides V tensor A with a left A action. And then because V tensor A is a left and right model, so this is also a B model. Specifically for mu, here we just use the co-product of A, and then we use the braiding to treat the second copy of A with V, and then we use the left action of V together with the product of A. And then we denote the resulting AB model by V both times A. And this construction actually gives us a functor denoted by L from the category of A model to the category of AB model. So the second one, in fact, by the same way, we can also construct a functor which operates in the reverse direction by considering an AB model M in our braided category, and another morphism mu that we have found here, and endows M with a left A model structure in C, and then we denote by tilde M the resulting left A model. And this construction, as I said, gives us a functor R, denoted by R, from the category of AB model to the category of A model, left A model, which assigns M to tilde M. And so with these two constructions, we then proved that the functor R is actually right adjoint to the functor L. And then we need to use a classical result is that then we have a C and D be K-linear abelian categories, and F and G two functors between the category, and with the fact that suppose that G is right adjoint to F, and we suppose that C has enough projective and that F is exact, then we have a natural isomorphisms between the eighth space. So I need to use it. So here, when we say that our category C and D be K-linear abelian categories, which means that our category are abelian in the usual sense, and each home set is a vector space. So now we can just use these two propositions to have the following corollary. So now, if we have a C is an abelian K-linear braided category with enough projectives and let A be a Hopf algebra in C, there exists a natural isomorphisms between the H space. And here, once again, we remark that because our category is an abelian K-linear braided category, and then our tensor by functors is supposed to be exact and K-linear, and then it follows that the category of a bimodal and the category of a modal are abelian K-linear. So we just return to this proposition. So we just need to replace our functor F by L and G by R. So we obtain the following isomorphism, and by using this isomorphism, we can prove that the projective of A as an AB model is less than the projective dimension of trivial model. And on the other hand, if we consider M now as an A model in our category, and we can endow M the right action by using the co-unit epsilon, and then now we have an A-B model. We just need to use our functor R to have a new A model in the category, and this new A model is actually isomorphic to M itself in the category of A model. And then we obtain the following isomorphism, where the second isomorphism here, we just need to use again the corollary here. So by this fact, we obtain that the projective dimension of trivial model less than the projective dimension of A as an AB model. And now we have the equality, the first equality here. And for the second equality, we just need to use the same reasoning, but we can work in the, we have to work in the reverse result category. So now, if we take C be our category, MH for H co-quasi-triangular Hopf algebra, we know that the global dimension is always less than the cohomological dimension, and which is the projective dimension of A as an AB model by definition. And this one is less than the projective dimension of A as an AB model, but in the category MH. Here, this inequality because we also have an adjoint pair functor, but it's not the same pair functor that we have found earlier, because here we omit H. And then this projective dimension equal to the projective dimension of K, because our corollary we have found it earlier with this fact. And then our question now is whether we have the projective dimension of trivial model as an A model in MH equal to the projective dimension of K as in the usual case, because if we have this equality on the dimensions are equal, so we can have our theorem. So to have these answers, we can work with the separable functors, as we will see here. We just we recall that if we have a C and D be two categories and let F be a functor between these two categories, then F induces a natural transformation denoted by P. And we say that F is separable if there is a natural transformation which operates in the opposite direction, such that P couples with M equals identity. So, and then we have also a classical result is that if we have C and D be two categories, K-linear abelian categories with enough projective objects, and let F be a functor between the two categories, and we suppose that F is exact, preserve projective objects, and also F is separable. Then for any object X in C, we have the projective of X equal the projective dimension, the projective dimension of X equal the projective dimension of F of X. And we also have some example of the separable functors, is that if we have H be a co-semisample Hopf algebra, and let A be a right H commodal algebra, then these focus functors are separable, and then we just combine these two propositions, we obtain our equality, our expected equality, is that we have the projective dimension of K A model in MH equal to the projective dimension of K as an A model in the ordinary case by using the separable functor. And then we have our main theorem that I introduced earlier, that let A be a Hopf algebra in the braided category of co-models over co-quasi-triangular, co-semisample Hopf algebra. We have all these dimensions equal. And then for now, I'm going to provide an example to see how we can use our theorem to find the cohomological dimension of braided quantum SL2. So, first of all, the definition of braided quantum SL2. If we take P and Q in K star, the algebra OPQ is the algebra presented by generator ABCD with some relation here. And here, if we have P equal Q, this is just the definition of our quantum proof in the ordinary case. And we then prove that OPQ is actually a KZ commodal algebra with the action denoted by our map delta here. And then actually we have as we have seen our example earlier, the category of KZ commodal is braided with the braiding given by with the braiding corresponds to the bicharacter of Z, the bicharacter psi of Z. And then we know that we have proved that our algebra OPQ is a Hopf algebra in this braided category with the structure similar in the ordinary case when we have a P equal Q. We have the same structure of Hopf algebra in the ordinary case. And then, so we want to, as I said, we want to find the cohomological dimension of OPQ. So by using our main theorem, we just need to find the projective dimension of trivial model. So first of all, we found that K have a free resolution which actually generalized a construction of Camel in 2005 in the P equal Q case. So thanks to this resolution, we have the projective dimension of K is less than 3. And then, if we take T in K star, we know that there is an algebra morphism, epsilon T, and then if T equals P Q minus 1, by some computation, we have found that the X space at the degree 3 is isomorphic to K, so it's not 0. So by definition, the projective dimension of K is greater than 3. And then combining by these two equality, we have the projective dimension of K is actually 3. So by using our main theorem, we have, because the projective dimension of K is 3, so the cohomological dimension of OPQ is also 3. And in our coming paper, we also prove that OPQ is smooth and is treated Calabi-Yau algebra by using some construction in about braided Hopf algebras, and which also finish my presentation here. Thank you for your attention.
So are there questions, comments?
Yes, please.
What about SLN for
I didn't hear the question.
What about SLN for n bigger than 2?
Oh, sorry, but I think that I don't know, because I didn't look for it before, so yeah. So yeah, I have no idea. Sorry.
Are there more questions?
Yes, please.
You stated 2 points that you have. 2 of the facts are classical, the things about adjoint things. Where do you, I have trouble finding stuff like this in the literature usually. Where do you cite these results from? Where do you find these classical results? This one, for example, the proposition.
This one, right?
Mm-hmm.
This one is proved by my supervisor in the case of treated separable functors. And this one, I have seen an article that the author have used, I think I'm not sure, but I just discussed with Laura later, but not her, maybe her father. They proved this fact in many different ways, but we have proved directly by using the Hall integral functor, Hall integral, because H equals semi-sample Hopf algebra too. So we can act. I do it actually.
So when you say classical, you mean these are from other research papers, they are not from textbooks? Yeah,
because this one is my supervisor.
I see.
He done in his article.
Yeah, this one result is in the Springer lecture notes that I wrote with Militaro and so, probably. And if I remember well, these are just applications of the Raphael theorem, where you can see when a functor is separable, if it has an adjoint, then there are easy conditions.
Yeah. Thank you. Thank you very much.
Any other questions? Comment? So if not, we have 10 minutes break. So our second speaker is Chiara Pagani from University Federico II in Naples, in Italy, and she will speak about Atiyah sequences of Hopf extensions.
Thank you. Thank you for the introduction, and thank you very much to the organizers for the kind invitation. It's my pleasure to be at this conference and in this beautiful city. Today I'm going to talk about a joint research with Paolo Schieri and Giovanni Landi, which is is a part of, it's about the study of ATIA sequences for Hopf-Galois extensions, and is part of a research project which aims at studying gauge transformations for bundles in non-commutative geometry. So the motivation comes from geometry, from non-commutative geometry. The setting is that of Hopf-Galois extensions. Hopf-Galois extensions are algebraic objects that were recognized to have a geometric nature by Schneider long ago. In particular, Hopf-Galois algebra extensions are encode the data of a principal action. If we have a G space, P, then sorry, I was told from home I don't see the pointer, so okay. If you have a principal action of a group on a space, for this talk we can think of the group as just a matrix Lie group, then this action can be detected at the level of the algebra of function on the total space. In particular, the algebra of function on P is a comodule algebra for the algebra of function on the group, and the corresponding subalgebra of coinvariance is a copy of the algebra of function of the orbit space. And also the fact that the action is free and transitive can be read at the level of the algebra of functions. In particular, it translates in the fact that OP is an Hopf-Galois extension of the algebra of function on X. As said, this geometric interpretation of Hopf-Galois extension is due to Schneider, then many people, including many people in this audience, contributed substantially to the development of the theory, especially in connection with non-commutative geometry. In non-commutative geometry, Hopf-Galois extensions really define principal bundles. In non-commutative geometry, a space is only defined via an algebra that morally is the algebra of function on the space. And if we want to define a principal bundle over an algebra, then we can use the definition of the Hopf-Galois extension. A principal bundle over an algebra will be the data of an Hopf-Galois extension of that algebra. In the following, I will always indicate with B the algebra that plays the role of the algebra function of the base space of the fibration, with A, the H comodule algebra that plays the role of the algebra function on the total space, and H will denote the Hopf algebra, the analogous of the structure group of the bundle. Now, let me give an example of this structure. A non-commutative example, an example of a non-commutative bundle. The example I give is the one which involves theta deformations, so-called theta deformations that were introduced by Kohn and Dubat-Violette more than 20 years ago. The example is the following. The total space, the algebra representing the total space of the bundle, is a theta deformation of the algebra of coordinate function of the spatial orthogonal group of 2n plus 1 matrices. It is represented as the algebra which is generated by some elements, 2n plus 1 square generators, which are subject to some commutation relations and satisfy some orthogonality condition. As we can see, the non-commutativity of the algebra, here I'm denoting with this dot theta the product in this non-commutative algebra. The relations of the generators depend on some real parameters. Are parameters of deformations. When you take all this theta to be equal to 0, what you get is a commutative algebra, which is nothing else than the usual algebra of coordinate function on the special orthogonal group.
Sorry, who is zeta with any indices?
Where is Z?
SO theta?
Theta is a deformation. This is a deformation of the algebra of coordinate function on 2n plus 1. Is here. Theta, yes. Theta, if you want, is the matrix of the theta ij. Yes, is a shorter way to write. Yeah, is a. No, you are right. If you want, this is a capital theta that is the set of all parameters. And in this case, this algebra is not just an algebra, but it has something more, since it comes from a group, is an Hopf algebra. And similarly, you can define the algebra, the theta deformation of the algebra of coordinate function of SO2n. And in the example I'm presenting, this algebra plays the role of the structure group of the bundle. In particular, what we have is an action, a coaction of H on A. That is, A is an H commodule algebra, in which way, in a very natural way, the point is that, exactly as in the classical case, you can realize SO theta to n as a quotient by an Hopf ideal of SO theta to n plus 1, the analogous of an homogeneous space, of a subgroup, sorry. And then you have a natural of algebra surjective map from SO theta to n plus 1 to its to SO theta to n r, to the quotient by the Hopf ideal, and by using this, if you compose this map with the coproduct of the Hopf algebra of A, you get the usual coaction, a coaction. So you have A, which is an H commodule algebra. You can look at coinvariance. If you look at coinvariance, what you get is that these are the generators Ni, with I going from 1 to 2n plus 1, and second index equal to 2n plus 1. If you think in matrix terms, these are the elements in the last column of the defining matrix of this quantum group. You have some commutation relations that, of course, come from those of the bigger algebra, and you also have a sphere relation satisfied by these generators who come from the orthogonality condition. This subalgebra of coinvariance is a copy, is nothing else, is isomorphic to the algebra of S2n theta, these theta spheres introduced, as I was saying, by Kohn and Dubois-Violette. And this construction results in a Hopf-Galois extension. In the classical case, the classical limit, when you take all theta to be equal, all parameters theta to be equal to 0, you get an Hopf-Galois extension which involves only commutative algebras, and is nothing else than the Hopf-Galois extension, which is associated to the frame bundle over the sphere. Time permitting, I will then use this example to exemplify the theory I'm going to present. Going back to the geometry, When you have a principal bundle, there is a notion which is very important, that is that of gauge transformations, or infinitesimal gauge transformations. Infinitesimal gauge transformations are G-invariant vertical vector fields on the total space. They do form a Lie algebra, and they are a module over the algebra function on the base space. In particular, they are the module of section of the adjoint bundle, the bundle associated to the principal bundle via the adjoint action of the group on its Lie algebra. And this Lie algebra is very important. In particular, what you can do given a principal bundle is not only construct this Lie algebra, but construct a sequence of Lie algebras. Associated to a principal bundle, there is a sequence, short exact sequence of vector bundles, where you have the adjoint bundle, the tangent bundle on the base space, and the Atiyah bundle. And when you pass to the module of section, you get a short exact sequence of Lie algebras, where here you have the infinitesimal gauge transformations. This sequence of Lie algebras is known as the Atiyah sequence of the principal bundle. Is named under Atiyah, who first introduced it. He was motivated by the study of connections and abstractions to the existence of connections in the complex analytic case. And it's of great interest, and it allows, in particular, for the study of connections in a simple way, somehow. When you look at a connection on the bundle in this setting, this is simply given by a splitting of the sequence. And also, it allows you to define the curvature in a very workable way. The curvature is just a measure of the extent to which the splitting fails to be a Lie algebra map. These infinitesimal gauge transformations and gauge transformations are really very important in classical geometry, bundle theory, topology, and so on. They allow for the definition of the moduli space of connections. So it would be very desirable to have an analogous notion in the algebraic setting and in the non-commutative setting. But so far, such a notion is missed. It's at least for non-commutative off-Galois extensions. If you take the off-Galois extension, which is associated to a principal bundle, the algebras involved are commutative, and you have a very, it's very easy, if you want, it's natural to define what are infinitesimal gauge transformations from the algebraic point of view. Instead of having vector fields of the space, you will have derivations of the algebra function on it. So infinitesimal gauge transformations for the commutative algebra function on the total space of a bundle would just be defined as derivations which are H equivariant, the analogous of the G equivariance, and which are vertical, meaning are zero when you evaluate on the subalgebra function on the base space. And this set is indeed a Lie algebra. Problems arise in the moment in which you pass to the non-commutative setting. In general, if you look for derivations in this classical sense for a non-commutative algebra, you may get very few of them. It's a condition that is too restrictive when you work with a non-commutative algebra. Similarly, is a problem which is very similar to that you have when you look for algebra morphism of a non-commutative algebra. So, it's clear that to define infinitesimal gauge transformations for non-commutative of Galois extensions, one has to change this definition, but it's not at all clear what should be the alternative, the non-commutative definition. And we don't have a solution, but we could find a solution to this problem dealing with a certain class of off-Galois extensions. The idea was to work with off-Galois extensions in which the algebras involved live in a braided category, then using the braiding of the category to define derivations. And the class of off-Galois extension we looked at are those we called K-equivariant H-Galois extensions. Are simply an off-Galois extension in which the algebra A, the algebra that represents the total space of the bundle, is a relative off module. In addition to the coaction of the off-algebra H, the principal coaction, also has another symmetry. That is, there is also another off-algebra, in principle different, another off-algebra that acts on it, and the two structures commute. A is a relative off-module. Examples of this kind of off-Galois extensions are quantum homogeneous spaces. In that case, K and H basically coincide. And another class of examples is that of two co-cycle deformation of off-Galois extensions, which are associated to classical equivariant principal bundles. This morning we had a nice talk by Brown in which it was recalled the theory of twist and two co-cycle deformation of off-algebras. This theory can indeed also be applied to the context of off-Galois extensions, and in particular from the point of view of non-commutative geometry. And with Paolo and some other authors, some years ago, we proved that indeed that theory of two co-cycle deformation can be applied to off-Galois extensions, and you can construct new off-Galois extensions out of others by using the two co-cycles. In particular, you can start from the commutative off-Galois extension of a classical bundle, use the twist, and obtain a non-commutative off-Galois extension. Actually, the example I presented before of the bundle on the 2n theta sphere lies in the intersection of these two classes of examples. We make a further restriction, that is to assume the K algebra, the off-algebra K, to be quasi-triangular. I don't need to recall that notion because we already had the dual notion of co-quasi-triangular off-algebra in the previous talk, and also of co-triangular off-algebra this morning. And also, I don't need to enter into the details because the fact was also recalled today that when you have a off-algebra which is quasi-triangular, the category of K modules is braided monoidal. The braiding, in this case, for a quasi-triangular off-algebra is basically given by the quasi-triangular structure. The idea is to use the braiding to define derivations of an algebra. That is, given an algebra which is a K module for K quasi-triangular, then we can define derivations by using the braiding instead of the usual flip to define them. As we know, if we are in the braided category of K-modules, we also have that morphism from an object to itself R a K-module. Inside this K-module, we can select braided derivations. Braided derivations will be maps from A to A which satisfy this condition. As you can see, when you take the trivial case, that is when R is trivial, you are back to the usual definition of a derivation of an algebra. These braided derivations can be defined in general, but if you make a further restriction that K is triangular, then what you have is that the braided derivations of the K-module algebra form a Lie algebra in the braided context. That is, you can endow your space of module of braided derivations with a bracket, which is a braided commutator defined by using the braiding, which is K-equivariant and also satisfy an antisymmetry and a Jacobi identity, which are defined similarly to the classical case, but again using the braiding instead of the flip. An object of this kind could be called a braided Lie algebra, or probably it's more correct to call it a K-Lie algebra. In the moment in which you assume K to be triangular, your category will become symmetric monoidal, so braided maybe is no longer the correct term. These kind of algebras in the symmetric category were studied by Manin under the name of S-Lie algebras. Here, what we proved is that the derivations, braided derivations of the algebra have this kind of structure. So braided derivations and the K-Lie algebra of derivations can be defined for any element, for any K-module algebra. In particular, we can take a K-module algebra which is the Hopf-Galois extension of some other algebra. And in that case, we can select two K-Lie subalgebras of the derivations. The first one is that made of derivations, braided derivations, which are also H-equivariant. The second one is that of derivations which are H-equivariant and also vanish on the subalgebra of coinvariant elements. What you can show is that both these spaces are K-Lie subalgebras, that are K-Lie algebras with bracket, which is simply given by the restriction of the bracket of their A to them. This K-Lie algebra is nothing else than a non-commutative version of the Lie algebra of infinitesimal gauge transformation of the bundle. So it's what we call the K-Lie algebra of infinitesimal gauge transformations of the Hopf-Galois extension. K is triangular. Notice that here we have realized how to behave this K-Lie algebra of infinitesimal gauge transformation as a sub-algebra, Lie subalgebra, of the H-equivariant derivations. So we have, by construction, an inclusion from out BA into their HA. Moreover, what we can easily observe is that if you take an element which is an H-equivariant derivation, since it is H-equivariant, it restricts to a derivation on the subalgebra of H coinvariants. So we also get a map from der HA to der B. So we get a sequence of K-Lie algebras. When pi is surjective, we get a short exact sequence of K-Lie algebras. This is a non-commutative analog of the Atiyah sequence of a principal bundle. And once you have that associated to your Hopf-Galois extension, you can go on with the construction, you can go on with the theory. In particular, you can talk about connections. A connection will be defined in this algebraic non-commutative setting exactly as in the classical case. A connection is a splitting of the sequence. That is a section of pi. Pi rho is the identity, is a map that goes from der B to der HA. Okay, here I don't want to go too much into details, but when your algebra, the base space of the bundle, is braided commutative, that is, satisfies this condition, then this is also a sequence of B modules, as you expect classically. That it's also a sequence of modules over the algebra function on the base space of the bundle. The connection is a section of pi, but doesn't need to be a Lie algebra morphism. In general, it's not, and the failure to be a Lie algebra map is measured by the curvature. In this context, in this setting, the curvature is just defined as rho of the commutator minus the commutator of rho. This is a classical fact. Here you need to be, of course, more careful in order to obtain something which is a braided two form, and so you need to define in a certain suitable way the commutator of maps of the rho. Okay, I skip the next slide, just the very last couple of minutes. I have 5 minutes, right? 4. It was 2 minutes. 2 minutes, perfect. Okay, so 2 minutes. Okay, going back to the example I was illustrating before, the Hopf-Galois extension over the 2n theta sphere. This is an example of a K equivariant Hopf-Galois extension. In this case, K is just the algebra of the n torus. And for that example, we construct explicitly the Atiyah sequence of the Hopf-Galois extension. In particular, we construct this Lie algebra, K-Lie algebra of infinitesimal gauge transformation. The construction is really explicit. We first construct this object, the derivations which are H equivariant. All of them are modules over the algebra function on the base space and can be represented as algebras generated by some generators with a Lie algebra structure, so a bracket which is explicitly worked out of the general formula I gave before. Okay, I don't have, unfortunately, the time to describe this construction, but I just want to say that you can explicitly construct the algebra, Lie algebra of infinitesimal gauge transformation, and once you have the Atiyah sequence of the bundle, you can study a connection. We were able to write down explicitly a principal connection on the bundle as a splitting of the sequence. When you have that, you can go on for this example, and you can study the Riemannian geometry of the theta sphere. That is, you can study connections, covariant derivative of associated, the analogous of associated bundles. In particular, the bundle that represents the tangent bundle of the sphere. And you can define a covariant derivative by using the map rho and also prove that is torsion-free and compatible with the metric. So we get a Levi-Civita connection for the theta sphere of Kondo-Violet. And I finish, and I thank you very much for your attention.
So are there questions, comments? Some questions? Please, Nicholas.
This in particular applies to K, the group algebra of C2, so this applies to super Riemannian geometry.
It can be applied, yes.
Do you know if this was done before or in that setting?
I don't know. It's probably something that's been done, but I don't know, honestly.
Thank you.
Any other question?
Just a comment on the previous question. For example, in the context of studying connections, this general scheme for studying connection has been applied to the super case, not necessarily the Riemannian geometry, just the differential geometry of connections, to study connections that are not even. And this is a recent work by Gabrowski and collaborators that was inspired by this way of looking at non-commutative geometry.
Any other comment? So if not, we thank the speaker again. So now we have a coffee break, and we resume in 40 minutes. Welcome back. So welcome back. Our next speaker is Paolo Aschieri from the University of Western Monte in Alexandria, and he will speak about metric compatibility and Levi-Civita connections of quantum groups.
Thank you very much. I'm very pleased to be in Ferrara at this conference, it's a series of conferences. And what I would like to talk about this afternoon is about actually a program concerning the study of the Riemannian geometry of the non-commutative algebras, and in particular of Hopf algebras. The main part of the talk will be based on joint work with Thomas Weber, that is here with us. And it's a paper just published in Journal of Algebra. But before going to the core of the paper, I would like to motivate and introduce this research field. So, on one hand, non-commutative geometry of quantum algebras is let's say, more established, well-established research field. We have a notion of differential calculi on an algebra, connections. If one takes connections on the bimodular of one forms, one can speak of torsion. We have a notion of curvature of a connection. These are quite accepted and standard in the construction, in the community. But coming to Riemannian geometry, some basic questions are still open. There are interesting examples, of course. And the basic questions are like, what is exactly a metric? That is, what is a symmetric element in the one forms, tensor one forms. And what is it, the metric compatibility condition that together with the torsion condition gives the Levi-Civita connection. So the idea is an approach to Riemannian geometry through the study of Levi-Civita connections. And as you see, these are open questions. Now, in the study of Riemannian geometry and quantum algebras, there are two approaches simplifying. On one hand, you can ask to consider metrics that are somehow compatible with the non-commutativity. On the other hand, you can consider metrics that are not necessarily related to the non-commutativity. In this case, you think of a metric more as a dynamical field. Let's give an analogy. If instead of quantum algebras, you substitute here homogeneous spaces, we go to that category, well, take for example a ball. Well, a ball is a round ball, it's a homogeneous space. The first metric you think on the ball is the round metric. But if you kick the ball, well, it starts oscillating. And if you want to describe oscillations and how it relaxes to the equilibrium, the round ball, well, you better know how to describe metrics that are far from the round metric. And here is the same. Instead of the G space, we have the non-commutative structure. That's the kind of structure we consider. And the similar analogy with thinking of a metric as a dynamical field applies to thinking as a connection, gauge field if you want, as a dynamical field. And here too, in the literature, there are bimodule connections that are basically connections compatible with the non-commutativity, and more general connections adapted to study dynamics. Now, very briefly, the discussion of the first approach, thinking of a metric that fits the non-commutative structure, goes back to many papers. I would like to cite here John Mador pioneering papers on the fuzzy spaces, Beggs and Majid approach, Bonvig, Goswami, Landi, Thomas Weber for H-covariant metrics, and Arnlind and collaborators for specific metrics on the theta sphere and the quantum spheres. On the other hand, on selected class, very specific class of non-commutative algebras, it is possible to describe a non-commutative Riemannian geometry where the metric is an arbitrary invertible symmetric tensor. These results that I'm sketching here have recently been incorporated in a more general theory that I would like to present you in the next two slides very briefly. So the context is that of considering a triangular Hopf algebra and the category, monoidal category of its representations. In particular, one considers an algebra A that is an H-module algebra and that is compatible with the triangularity structure, meaning the product, the multiplication is commutative via the R matrix. Well, in this context, there is a canonical way to construct a differential calculus. There is a canonical way to define a metric as a braided symmetric non-degenerate element, braided with respect to the R symmetry, that is a representation of the permutation group in this case, and to extend connections to connections on tensor product of modules. You see, it's using the braiding if you want. Well, in this context, then, it is possible to have existence and uniqueness of the Levi-Civita connection. This then leads to a notion of Ricci tensor, of scalar curvature, and to study Riemannian geometry. The key point in this construction, on one hand, is to use this sum of connection or connection on tensor product construction that is general, does not require a bimodule connection. And the other is to recognize that when dealing with non-commutative algebras, you frequently have to consider operators from the left and operators from the right. And it turns out that covariant derivatives have to be constructed with the vector field, covariant derivatives along vector fields, with the vector field acting from one side and the connection acting from the other. It's something a bit unexpected, but everything can be worked out consistently. In particular, these examples include all non-commutative algebras arising from the infrared-Tugo cycle twist deformations, so all kinds of algebras Ken Brown was discussing earlier this morning, for example, but also any cotriangular Hopf algebra, because a cotriangular Hopf algebra is automatic, a braided commutative algebra in a given category. In particular, recently, having fun constructing the Riemannian geometry on 2 copies of Zwiedel H4 algebra, so it's everything can be worked out very explicitly. Now, coming from this setting, I asked, together with Thomas, and of course, with some hints and suggestions from the community, to see whether we can go beyond this symmetric monoidal category setting that is the one associated to triangular R matrices. Notice that this setting is anyhow interesting. It's an interesting generalization of usual differential geometry within the symmetric monoidal category is Z2 graded supergeometry with its supersymmetry groups. And here we are extending it to this non-commutative geometry. But let's go and try to go beyond this and to go to quasi-triangular structures, or even not consider such constraints. And what I would like to tell you about now is the study of Riemannian geometry and Levi-Civita connection on quantum groups like SLQ2 or their homogeneous spaces. Indeed, quantum groups like those of the ABCD series are prominent examples of non-commutative geometries. And in particular, we will study the definition of metric compatibility and provide some existence and uniqueness theorems. So, what we are interested in is providing existence of Levi-Civita connection for a metric that is not the round metric, the killing metric, let's say, on the quantum group. And we will see that indeed we find a one-parameter family, a 1 degrees of freedom matrix on SLQ2. And the main tools for this construction are again on one hand the sum of connections on tensor product of modules construction, and on the other the ability to consider a direct sum decomposition of tensor one forms into symmetric and antisymmetric. So, entering more into the core of the topic, let me discuss the bicovariant bimodules that are the building blocks of the differential calculus on Hopf algebras, as discussed by Voronovich. Let's then discuss the sum of connections, how the direct sum decomposition takes place according to a canonical braiding that exists in bicovariant bimodules, and finally come to quantum Riemannian geometry. Are there any questions? Okay, so I consider a Hopf algebra with invertible antipode on a field. There is a canonical way to construct a bicovariant differential calculus on such Hopf algebra. Bicovariant here means that there is invariant under the left and the right action of the group on itself, or dually the Hopf algebra itself. And in particular, this construction gives the bimodule of one forms, what I call omega 1, as a left H module, a right H module, compatible with comodule structures, left and right. Then the category of bicovariant bimodules is a braided monoidal category. This can be, for example, seen comparing it with the Jeter-Drinfeld category. There is an isomorphism. Schauenburg discussed that. And the braiding is very simply given. I take a right invariant one form, I take a left invariant one form, they swap as a flip, and then is extended as an A bimodule map, where H bimodule map. It's furthermore a closed braided monoidal category. The home functor exists, and is equal exactly to right H linear maps. Morphism here are right H linear, left H linear, right H collinear, left H collinear. Here we are just stating right H linear maps. This exists because we are on finitely generated bicovariant bimodules. Then we can state this equality. Well, in this talk, I will use this notation for the braiding with the indexes alpha and alpha. And the space of maps right H linear from M to N has this bimodule structure. Well, said that, there is, given indeed a map phi that goes from M to M prime. It's too slow. And another map psi that goes from N to N prime. One can construct a map that goes from M tensor N to M prime tensor N prime. And this map is constructed via this, in this way. It's called the tensor sigma omega for W for Voronovich. Is defined here, and is indeed a morphism of bicovariant bimodules. This is an interesting map because it allows to define what is, for example, the sum of two right H linear maps. It's written here. So to implement, if you want, the Leibniz rule in this context, when you have a tensor product of modules, it's done using this map, and therefore is done using the braiding. Now, when you consider a connection on the space of one forms, and you want to lift it to the space of one forms, tensor one forms, or in general to the space of tensor fields, you have to lift it. And you usually use the Leibniz rule. Now, we want to use the Leibniz rule consistent with this braided monoidal category. If we have right H linear maps, that's the Leibniz rule to be used. But connections are not right H linear maps. Connections are just linear maps. They satisfy the Leibniz rule. So we have to extend this construction to a category that is much bigger. Instead of considering right H linear maps, home H, we have to consider simply linear maps, homes. Is this possible? It is. I would like to explain the construction. So the point is we can just, for simplicity, concentrate on the category of H comodules and look at linear maps there, K linear maps there, Well, this category can be proven to be a closed category, where the Hom in order to construct the Hom functor, you have to consider rational morphisms, but this is a procedure that can be considered. And the result is that with such construction of rational morphisms, this category is a closed monoidal category. Then the next thing is, considering this rational morphism, try to lift to this more general setting the product of morphism that we were seeing before. And here is how to proceed. First of all, we have the braiding isomorphism due to the presence of the braided monoidal category of bicovariant bimodules. Now, we are back in bicovariant bimodules, okay? But we lift this map to a map, you see, where the tensor product is over K, is no more over the Hopf algebra H itself. And one lift is the following one. It's an arbitrary splitting of lift of this tensor product. Well, with this definition, we have that the map sigma is a morphism just in this category, not in that of bicovariant bimodules. You see an H is missing here. Is middle linear with respect to H and satisfies just one of the two hexagon equations. Associated to this map, we then can construct the following maps that, given two linear maps between M and M prime and N and N prime, associates a morphism here. The definition is given here below, and you see it is using exactly this half braiding that I've been discussing here. This is sigma here. And the property is that this map is a well-defined map in the category of bicovariant bimodule. This map is associative and is a morphism in the category. Well, out of this map is, first of all, one can immediately see that the maps actually naturally descends to the tensor product over H here, and then it can be projected to end up in the tensor product here. So out of this map, it's possible to construct this map. And this is the map we are using, and we will be using, and this morphism in the category of bicovariant bimodules. We call it tensor hat. Now that we have these basic ingredients, we can construct the sum of connections. So let's recall a connection, a right connection on a module is a map that satisfies the following Leibniz rule, where this is the differential calculus of forms. These are the forms. It can be extended to higher forms in this way that is the usual differential geometry way. But now we have an understanding of this formula abstractly, where each term is a well-defined element, is a well-defined map, exactly because we constructed this tensor hat map. The curvature and the torsions are canonically defined. Connections on Hopf algebras are present. There are, in particular, a canonical connection that is invariant and that is right and left collinear, and is determined by asking that the left invariant parts of the module is 0. And then there is another canonical connection that is flat and that is constructed via the structure constants, like in usual group theory. Well, we have proven that connections are rational morphisms. So all the theory before applies. And finally, we define the following sum of connections. This is a well-defined sum, and moreover, as an extra consistency check, the canonical connection on module M and on module M sum exactly to the canonical connection on the tensor product of modules. I skip the linear algebra condition. Just let me say that when you have a braiding coming from the ABCD series, this braiding is diagonalizable, so there is a canonical way to split tensor product in a symmetric and the rest that we define to be the antisymmetric ones. This goes dually to the space of vector fields. And then, according to this splitting, we have a splitting of the connection in a connection on antisymmetric forms, a connection on symmetric forms, and two right H linear maps, the off-diagonal maps here, according to this direct sum decomposition. Everything is compatible with duality, and once we have done this analysis, we can define what a Levi-Civita connection is. First of all, a metric. A metric is an invertible element, symmetric in vector fields, tensor vector fields. This V stands for symmetric, while the wedge stands for antisymmetric. And the connection is Levi-Civita if it is torsion-free and it's metric compatible. But notice that metric compatibility is not required for the whole connection. It's just the antisymmetric component that is required to be metric compatible. Well, associated to these definitions, we have an existence theorem. Suppose the following map that is well defined and constructed out of a metric is invertible. Then if the following map is invertible, there exists one and only one metric compatible connection. And the formula is the following. You see, you take the canonical flat connection on the Hopf algebra. Then you correct it by a term that tests exactly how much the dual of the canonical connection, flat connection on the Hopf algebra, fails to be metric compatible. It can be proven that this is a metric Levi-Civita connection and is unique. What's next? Well, this can be kind of compelling to prove invertibility of this map. But for specific metrics, it's quite easy. And the specific metrics are the metrics that are central and invariant under the group actions. Well, this is somehow an easy result, but we go back to the very specific case where the metric is very rigid, okay? But all these, if you want, categorical study of the construction of how connection sums allows for a nice result that I would like to explain now. Suppose that there is a central metric and an invariant metric. Then a Levi-Civita connection exists if simply this map associating just to the braiding, so independent from the metric, is invertible. And for any other metric that is differs from the original one by a function, an invertible function, so a scaling, a Euler scaling. So here we are introducing a lot of freedom because f is really a function on the quantum group. Then we have the following expression for the Levi-Civita connection. So this result in particular enables us to say that since on SLQ2 there is a central B-invariant metric, since on SLQ2 the map pi is invertible and hence also the map phi is invertible, we have a one degree of freedom family of metrics on such quantum groups that satisfy the Levy, we have 1 degree family of Levi-Civita. We have Levi-Civita connections associated to a 1 degree family of matrix on SLQ2. I think that this is a hint that there is quite a landscape to explore in these directions, and I'm looking forward to work out more examples, like, for example, the Borel quantum subgroup of SL2. That's nice because it's two-dimensional, the tangent space. And why not? Previously I was speaking of the Riemannian geometry of Zulidler-Hopf algebra, and here one can study the Riemannian geometry of Taft-Hopf algebras and see what this extra structure tells us about the algebra themselves. Thank you very much for your attention.
Okay. Are there questions, comments? Okay, if not, we thank the speaker again. We resume in 5 minutes. So our next speaker is Thomas Weber from Charles University in Prague, and we will speak about infinitesimal braidings and pre-Cartier variations.
Okay, thank you. So first I would like to thank all the people who make this conference meeting possible. I'm very glad to be here and also grateful that I can give a talk. So the story that I will talk about here is based on some project that I have with 3 people that are in this audience here. One is sitting in front, 2 of them are sitting in the very back, they are hiding, yeah. And yeah, we also managed to publish this quite recently, so I'm curious what you think about it. Okay, so let's say the idea that we had in mind is what would be a good definition of a first-order deformation of a braiding, or what we could call an infinitesimal braiding. And yeah, now I will tell you what the outcome is, so what we think is a good definition. So let me motivate this first a little bit by the category algebra correspondence that I think guides a lot of our thinking and that we have heard also partially in this conference. Yeah? So starting with an associative unital algebra, let's say over a field, we can look at a category of left-H modules, and then we know that this category is monoidal if and only if our algebra is actually a bi-algebra. It is a braided monoidal category if and only if we even have a quasi-triangular bi-algebra with universal R matrix R. And yeah, this was the known part. Now what we added to the story is another thing, so what we call a pre-Cartier category. So this, on the algebra side, the corresponding animal would be what we call a pre-Cartier bi-algebra. So here we do not only have a bi-algebra with a universal R matrix, but we have also this chi here that we call an infinitesimal R matrix. And just as we have seen that the R matrix corresponds to sigma, to the braiding, we have that chi corresponds to T that we would call an infinitesimal braiding. So that's written here. So basically sigma is given by the action of R with some flip, while T is given by the action of chi. Okay, I think in this conference I don't have to explain what a braided monoidal category is. I think everybody knows. So we have some tensor product here. We have some natural iso that satisfies the 2 hexagons. And then you can prove that also the braid relations are satisfied. We have also seen in the talk of Ken Brown how this corresponds to R matrices and triangular, or in our case, quasi-triangular structures. So if you start with a bi-algebra H, we see that the category of left H modules is a monoidal category where the action on the tensor product is simply given by the coproduct. And this is an action exactly because delta is an algebra morphism. Very good. Then Drinfeld and Majid showed around 1990 that this category is braided now if and only if H is quasi-triangular. We have seen the definition several times, so I will just show you very briefly and recall that the braiding sigma is really given in terms of the R matrix, and this goes both ways. Yeah? Furthermore, let me note that the symmetric case, this would be when sigma squares to 1. This happens if and only R is triangular, so if the inverse of R is given by the tensor flip 1. And that's a special case that's interesting, as we have seen in several talks of this morning and afternoon, even though here we can work in a more general setting where we could take any braiding or any universal R matrix. Just very quickly some examples so that we see the theory is not empty. So every commutative bialgebra is a triangular one where we can take the R matrix as just one tensor 1. So this works for any group algebra, for any group, or any universal enveloping algebra for any Lie algebra G. On the group algebra of the cyclic group, something special happens. There we can take the quasi-triangular structure given by this formula here. That looks a bit scary, but you can check all the properties. It's not so difficult. In particular, for n equal 2, we get the super geometry braiding. So that's the usual sign factor you get in super geometry. Another class of examples that is interesting is the Drinfeld double for a finite dimensional Hopf algebra, where you get as the R matrix simply by summing over a basis and the dual basis. Those are the small EI up and down index. Okay, many quasi-triangular structures. So now to the new part. Let's motivate a little bit what an infinitesimal R matrix should be. So we start with a bialgebra H, and we look at the formal power series in a parameter H bar. This is a topological bialgebra where you simply H bar linearly extend everything. And you have to be a little bit careful, but I skip over all the technical details here. This is a topological bialgebra. We call it H tilde. And let's say on this H tilde, you have an R matrix that we call R tilde. What you get from this is that in zero order, you have to have also an R matrix for H. Yeah, this is this H telling us that HR is a quasi-triangular bialgebra. In particular, R is an invertible element, so we can factor out R, which means then we can write R tilde as R times 1 tensor 1 plus something in first order that we call chi plus higher orders. And our question was, what are the properties of this chi? Yeah, what does it satisfy? And this led to this definition here that now is completely independent of the formal power series part. So this just works for any bialgebra. So we say that this triple H R chi is a pre-Cartier bialgebra with an infinitesimal R matrix chi. It's just an element of H tensor H. If, first of all, HR is a quasi-triangular bialgebra, and this chi satisfies the following properties. We have some commutativity with the coproduct, and these two equations here that I would call some braided Leibniz rules. Later on, we are going to see a bit more what those mean. Yeah. Furthermore, so if R chi equals chi of R, we call this triple a Cartier bialgebra, so no pre. Okay, what is the corresponding categorical counterpart? So this goes back now to the first motivating slide that we saw. We have this little proposition that tells us H R chi is a pre-Cartier bialgebra if and only if the corresponding category of left modules, first of all, is a braided monoidal category, but also has this extra natural transformation T that satisfies these two Leibniz rules that just look like the Leibniz rules on the previous slide. And if we have a Cartier bi-algebra, so R chi equals chi of R, so this happens exactly if the braiding commutes with this transformation T. If we have now a braided monoidal category with a natural transformation T satisfying all of this, we call the category pre-Cartier category. And T is the corresponding infinitesimal braiding. Okay, that's a lot. Some comments on the definition. Some special cases were known in the literature, namely for symmetric braidings, where in addition, sigma T equals T sigma, we get back the known notion of a Cartier category that was discussed in these papers and books here. So that's why we choose the pre in the definition, because our definition is more general. And yeah, still we have to justify why it's interesting to look at this more general theory. So let's justify it now afterwards. Why is it interesting that we look at these animals? First of all, examples. A trivial one is always good. So infinitesimal R matrices form a vector space. So for a fixed quasi-triangular bi-algebra, they form a vector space. So this also tells us we can always take chi equals 0 and all of this works. But okay, that's kind of the trivial way to get one. A more interesting one is if we start with a quasi-triangular Lie bi-algebra. So just to recall very quickly, this means I have a Lie algebra and I have a classical R matrix. So an element small r in G tensor G that is ad invariant and satisfies classical Yang-Baxter, written here. In this case, we can simply symmetrize R, and this gives us a chi, so an infinitesimal R matrix for the bi-algebra or Hopf algebra UG with R matrix 1 tensor 1. So this gives us a huge class of examples. Another class, maybe I can skip this, or okay, in the commutative case, this definition basically boils down to chi being in primitive tensor primitive. So that's kind of why I called it a braided Leibniz rule. So in some more classical situations, the definition of our chi just boils down to chi being in primitive elements, tensor primitive elements, which means that in some cases you cannot find many infinitesimal R matrices. For example, for the group algebra, only chi equals 0 works. So this is a notion that is better suited for quantum groups, as we are going to see later. Okay, maybe slightly more interesting example is Sweetler's 4D Hopf algebra that also Paolo mentioned at the very end. So I'm pretty sure most, if not all of you know, that's the algebra generated by G and X, where G squares to 1, X squares to 0, Xg equals minus Gx. G is group-like, X is twisted primitive. And for this Hopf algebra, it is known that all quasi-triangular structures are actually triangular, and they are of this form here. Horrible formula, but still manageable. So what we did, we classified all the possible infinitesimal R matrices, and it turns out that for this, the formula is pretty small. They have to be like some complex number times xg tensor g. Those are all of them. And in particular, the only way this is Cartier, meaning that I have this extra compatibility of R and chi, is when chi is 0. So this tells us that even for this Hopf algebra, it makes sense to look at the pre-Cartier structures rather than the Cartier ones, because for the Cartier, only the trivial one would work. Just mentioning, so there's a more general example given by the Redford Hopf algebras. So this ENs here, this would give Sweetler's Hopf algebra as E1. And also for those, we classified all possible infinitesimal R matrices. So this is work in progress, maybe published soon, I'm not sure. Work by 3 guys here in the back. Yeah? Okay, later on we are going to see some other non-trivial examples coming from FRT. Okay, so I'm probably a bit slow, but let's see, maybe. Okay, maybe let's prove some theorems. So apart from
examples, we can also show that these infinitesimal braidings or R matrices have some interesting properties. And so the first thing we could check is, if you start with a pre-Cartier quasi-triangular bialgebra, you can show that the chi is automatically a Hochschild 2 co-cycle. So it satisfies this equation here. And furthermore, chi satisfies what we called the infinitesimal quantum Yang-Baxter equation. This is this horrible looking thing here that is basically just the usual quantum Yang-Baxter where you shift chi through all possible position. Yeah. Anyway, part of this was known for the special case that we have seen UG with R matrix 1 tensor 1 and the infinitesimal braiding coming from a quasi-triangular Lie bialgebra. But this was really the only thing we could find studied in the literature, and apart from this, nothing more general was known or looked at. So we have the much more general proof. So this is for the co-cycles. What happens for the, so can we also get some co-boundaries in some cases? Yes, we can. So if we ask more, so first of all, if we not only have a bialgebra, but also a Hopf algebra, so an antipode, we can build this gamma here by just taking chi as, of course, being a finite sum over chi I up, tensor chi I down, apply the antipodes to the first tensor and multiply, you get an element in H. You can show it's automatically as a central element. And for a certain reason, we call this the Casimir element. Then we showed that, okay, in the case where it's not pre-Cartier, but Cartier, and we have a triangular Hopf algebra, then chi is not only a co-cycle, but it's even a co-boundary, and it's exactly the image of the Casimir under the Hochschild differential. So that's what's written in this proposition. Okay, so we have an understanding of the chi. There are some Hochschild co-cycles, and in some cases there are even co-boundaries. Okay, maybe here I can go a bit quicker. So we can, given some of these pre-Cartier bialgebras, we can get many of them. One simply kind of pushing forward via an algebra morphism. The other one is like building tensor products. And the third way would be using Drinfeld twists that we've also seen in Ken's talk. So if you have a Drinfeld twist, definition is given here, we can simply twist everything and use, starting with a pre-Cartier bialgebra, you also get one as the twisted one. Okay, the dual thing, universal R forms, I can also be very quick because we have seen this now also in several talks. So we started like with modules. Now if you want to talk about co-modules, you should look at co-quasi-triangular things rather than quasi-triangular ones. Here's just a definition that tells us that starting with a co-algebra, the category of right H co-modules is braided monoidal if and only if H is a co-quasi-triangular bialgebra with a universal R form satisfying these properties that are, I mean, we've also seen in the previous talk, so I can simply skip over this. Here's written what the convolution inverse is, all of you know. Yeah, maybe here just commenting using the convolution product that we write star, we can write those axioms in a nicer element independent way, and then what you see on the bottom here is just the axioms of a universal R form. And okay, this would be a co-quasi-triangular structure if also the convolution inverse of R is just the opposite one, then we call it co-triangular. Okay, we've also seen this, so how the category of co-modules becomes braided, so you know how to coact on the tensor product, and the braiding again just uses the coaction and the universal R form. And okay, we simply by definition say that an infinitesimal R form is the algebraic structure that makes the corresponding, that corresponds to the infinitesimal braiding for this category of right H comodules. Spelled out explicitly, it tells us that an infinitesimal R form for a co-quasi-triangular bialgebra is a K linear map. I still write it like chi from H tensor H to K. That convolution commutes with the product, mu is the product, and that satisfies these braided Leibniz rules now corresponding to the product and to the convolution product. And this is then what we would call a pre-Cartier co-quasi-triangular bialgebra, while if we have in addition that R convolution chi equals chi of convolution R, it's a Cartier one. And all of the statements we have seen in the module and quasi-triangular case go through to this dual co-quasi-triangular setting. Okay, another example is quantum 2x2 matrices. So now we are getting closer to quantum groups. So just to recall very briefly, so MQ2 is the algebra generated by some alpha, beta, gamma, delta modulo de Manin relations that are written here. It's a bialgebra using the usual matrix co-multiplication and unit matrix as the co-unit. And it's also known that this is a co-quasi-triangular bialgebra if we take the following R matrix defined on generators here. Very classical stuff. And okay, we showed that for these quantum 2x2 matrices, we can find a non-trivial infinitesimal R form that we write here as partial Q tensor partial Q. And this makes the bialgebra into a Cartier one. So we have even that R chi equals chi of R. And here just very briefly, what happens is this partial Q takes a homogeneous element of degree xi and maps it to degree times epsilon of xi. This is the correct thing. I think because there's not much time, I'm going to go through this very quickly. So the quantum groups GLQ2 and SLQ2 are then quotients of the quantum 2x2 matrices, and we show that on a GLQ2 we can still find an infinitesimal R form, while on SLQ2 we showed that the only one you can get there is the 0 one. So we still don't really understand why for some quantum groups there's a lot of freedom, while on others we simply get 0. It's a bit weird. I don't really understand the reason, but yeah. Anyway, this is what we proved. Okay, maybe now an interesting result, maybe the last thing I want to tell you about is this FRT, named after Faraday, Freshettiken, and Takhtajan. That's okay. I tell you what is this classical theorem about. It says that if you start with a braided vector space, so a tuple V and C, where V is just some vector space and C is some endomorphism of V tensor V that satisfies the braid equation. You further want that V is finite dimensional, let's say with a basis V1 until Vn. And you take n squared in the determinants Tij. You look at the corresponding free algebra of the Tijs. It's automatically a bialgebra if you take simply the matrix coproduct and epsilon being the Kronecker delta. Now you take the coefficients of this endomorphism C. You call them C, I, J, K, L. A lot of indices. I know it's scary, but we can go through it. And we denote by IC the two-sided ideal in the free algebra generated by these capital C's. So it's basically the C is on the left minus the C on the right, and in both cases you sum over M and N. Okay, you look at the quotient algebra, and it turns out it's not only an algebra, it's even a bialgebra. And furthermore, this bialgebra is coacting on the vector space V. FRT then proved that for each finite dimensional braided vector space, there is one and only one co-quasi-triangular structure R on this quotient bialgebra that has on generators the coefficients of C. Yeah, so that's a way to get a lot of co-quasi-triangular bialgebras. And in fact, like all of the quantum groups that we know and love, they come from this machine. A question that we had is that, okay, can we do a similar thing for the infinitesimal R forms? So can we find another endomorphism, let's call it T, which gives us a chi, possibly on a double quotient? And what does this T has to satisfy? And okay, I think this is the last thing I want to tell you. So here, since time is short, in this one slide you can see how FRT got their R matrix font, and the very rough idea is that on the free algebra you define R simply as having the coefficients of C on generators, while you extend it via the hexagons. Yeah? So you're saying if you have the product of two T's, then the extension is done via the hexagons. Yeah? And then you have to quotient by this ideal IC in order to get the quasi-commutativity of R. Okay, that's very roughly how FRT works. And we did the same thing for our chi. So starting with a braided vector space where we have the corresponding R matrix on the free algebra, let's start with any endomorphism T on V tensor V. Let's write the coefficients here, again with T, I, J, K, L. And define on the free bialgebra your chi as having the coefficients of T on generators, being trivial if there's a 1, and extend it via this braided Leibniz rule. I mean, you can do that. What we showed is, first of all, this makes sense. You can do that, and it gives you a well-defined map on the free algebra. And so here, this automatically satisfies these braided Leibniz rules on the free algebra. Now, we further have to impose the commutativity with the product, and this has to be done on a certain double quotient such that R is still a co-quasi-triangular structure on this double quotient. So many things have to be taken care of. How to do this? And okay, here's just reminding the setup. So now from the small Tij MNs, we build this another two-sided ideal that we call IT in the quotient AC that is now given with the small t on left and right rather than the small c. And we quotient via the second ideal. We get a double quotient that is by definition an algebra. We showed that first of all it's a bi-algebra, and moreover R descends to a co-quasi-triangular structure on this double quotient if and only if the following two equations hold. Okay. Furthermore, chi descends to, first of all, a map on this double quotient if and only if these other two equations hold here. So those are not independent. You can somehow mix them up in a certain way. And so the best thing that we found is this 1 and 2. And so this is what we made into the definition. So we call this an infinitesimally braided vector space. So you start with a braided vector space VC, and you also ask for this extra endomorphism T satisfying 1 and 2. And this looks really complicated and horrible and whatnot, but we can make sense of this for some special cases. First of all, if C is simply the tensor flip, 1 is trivial. How much time do you have? 1 minute, okay. I have 3, okay, but then I'll be really quick. So if C is simply the tensor flip, then 1 is trivially satisfied, while 2 becomes what is known as the infinitesimal pure braid relations that were studied, for example, by Kono. So that's something that is known. Furthermore, I would like to stress that you can, starting with a braided vector space, 1 and 2 are trivially satisfied if you take multiples of the identity for T, and we also know for some special cases how to solve them. No time to talk about this. The outcome is that we show if you start with such an infinitesimally braided vector space, then we show that there is one and only one pre-Cartier co-quasi-triangular bialgebra structure on this double quotient that has the Tij's on generators. And there's some special ways of solving it that gives, for example, this MQ2 that we have seen previously. There's also a proposition that says also the other way around is true. So starting with a pre-Cartier co-quasi-triangular bialgebra and a left co-module, we get an infinitesimally braided vector space in this way here. So it really tells us that the two things are the same. That's quite nice. And I think since my time is over, I cannot tell you about Tanaka crying, but just saying we also have that. And okay, thank you for your attention.
Are there questions? Please, go ahead.
It's not a question. I would like just to mention that... Sorry. It's not a question. Thank you for your nice talk. I would like just to mention that, that Pierre Cartier died two weeks ago. Then let us have a thought for his memory.
Very sad.
Any other comment? Okay, if not, we thank the speaker again. Okay, wait. Go ahead.
So, can you repeat? I don't know whether you said what would correspond to the finite deformations. These are infinitesimal deformations. So, what would be the finite version?
So you're asking for what would be the first order deformation of a braiding? Or did I get it right? No.
These are infinitesimal deformations of a quasi-triangular, associated to a quasi-triangular structure. Mm-hmm. Do you have a notion of what would you expect to be the notion of a finite deformation?
Finite what? Sorry, I didn't get it.
Not infinitesimal. How do you? Can you integrate these infinitesimals?
Okay. Very good question. We thought about this, and I mean, sorry. Yeah. So part of the future projects would be exactly this. So there's a natural deformation question, yeah, that says if you are given such an infinitesimal R matrix or R form, is there a way to get a fully fledged one on formal power series? So can you, as you say, integrate or deform zero order plus first order to higher ones? And this works in some very special cases. For example, for Sweetler's Hopf algebra, you can simply take the, what's written here, this R tilde being R exp h bar chi. This works very well, but only because Sweetler's Hopf algebra is very small. For higher ones, this is probably not going to work. And yeah, we think about that. And it should be connected somehow to Ettinghoff-Kashtan quantization of quasi-triangular Lie algebras. I hope this answers partially your question. I'm not sure.
Okay, so you can continue the discussion afterwards. So we thank the speaker again. And we resume in 3 minutes.
So, I'm glad to announce our last speaker today, Professor Vladislav Karchenko from the Autonomous National University of Mexico in Mexico City. And he will speak about quantizations as quadratic linear Koszul algebras.
Okay. Thank you very much for the invitation to give this talk. So the title is Quantizations as Quadratic Linear Koszul Algebras. I would like to present 3 theorems in my talk. The first one is this one. The multi-parameter quantization UQ SL n+1 plus in Q-Weyl generators is a quadratic linear causal algebra. Theorem 2, the multi-parameter quantization UQSO to n plus 1 plus in QVL generations is a quadratic linear causal algebra also. But this is SLS Lie algebras of type AN, SO is the Lie algebras of type BN. And theorem 3 says that two-parameter quantization UQG2 plus in QVL generators is not a quadratic linear causal algebra. So we have these three results. Now I would like to explain for you what means every word in these theorems. What does it mean quadratic linear causal algebra? What does it mean quadratic causal algebra? And so on. And why it is interesting to consider these problems. Also, I should explain what does it mean QVL generators. Why I'm interested on this problem? So how the Greenfield-Jimbo quantization was defined? If we have a Lie algebra, Katz-Moody Lie algebra, so we have embedding of this algebra in universal enveloping algebra. And Greenfield and Jimbo, they define the deformation of this universal enveloping algebra, so they get the quantum algebra UQ, quantization UQ J. But it is very interesting to define quantum Lie algebra in a standard way, so that here we have this something which we should call quantum Lie algebra, and so we have the construction of universal enveloping algebra, and we get the same algebra UQJ. Now we have this UQJ, how to define this quantum Lie algebra. This problem in different ways. There are not the only way to resolve this problem or to look at this problem. And so there was a paper by Majid in 1994, Deleuze, Hoffman in 1996, Lubashenko, Sudbury in 1998, Deleuze, Gradner, Golut in 1998, Bautista Ramos, Juarez Ramirez in 2001 and 3. The approaches are very difficult. The idea that we shall discuss here is the following. We will consider the Poincaré-Birgoffi theorem like the basis for the definition. So we should do something like inverse problem of the construction of Poincaré-Birgoffi generators. So we have here as this algebra. We should find this the linear subspace, finite dimensional linear subspace, so that the basis of this subspace is the set of Poincaré-Birgoffi generators. This idea, the point is that it is known that this algebra really has the Poincaré-Birgoffi basis. But the point is that even the Lie algebra, it is not possible to recover from the universal enveloping algebra just by this property, because there exist Poincaré-Birgoffi generators which do not belong to this Lie algebra. But there is a very important property that if we consider universal enveloping algebra as an algebra generated by a basis of J, so the universal enveloping algebra is a quadratic linear causal algebra. And this is the motivation of our investigation. Is it through the same statement for quantizations? So I would like to remind what does it mean, recall what does it mean Kazul algebra, quadratic Kazul algebra. The quadratic Kazul algebra appeared in a paper by Prigi in 1970. The paper is called Kazul Resolutions, Transaction of the American Mathematical Society. And so he called this quadratic Kazul algebras, but in fact this construction is belonged to Pridi. The Kazul algebras in fact arise in many areas of the modern mathematics: algebraic geometry, representation theory, non-commutative geometry, topology, number theory, theory of pseudo-roots of non-commutative polynomials, and also in theory of quantum algebras. There is a beautiful book of Polishchuk and Positetsky, quadratic algebras, where one can find all the terminology belong to this theory. I would recall a little bit what does it mean quadratic Kazul algebra. So we have free algebra, and we have an ideal of relations, which is ideal. This is the space in the V tensor squared, the set of quadratic polynomials, and in free algebra we consider an ideal generated by this space. And the definition of quadratic Kazul algebras is complicated, and there is lots of equivalent characterizations, and one of them belonged to Bekelin in 1981. A quadratic algebra I is Kazul if and only if for all n greater or equal than 3, the collection of the subspaces, this is subspaces, in fact this is subspaces that span the ideal of relations, generates a distributive lattice with operations supremum as A plus B and infimum as A intersection of B. And so we may consider this like definition of quadratic Kazul algebras. No, this is, we have here where appear these spaces x1, x2, xn minus 1. What does it mean, Weyl basis of Lie algebra, of classical Lie algebra? We have a set of simple roots, alpha 1, alpha 2, alpha n. To simple roots correspond the generators x1, x2, xn. To each positive root, which is sum of the simple roots, in such a way that all partial sum in this long sum is also root, is also positive root, and so to this element corresponds a basis element, which has this form, just commutators, long right ordered commutators. If we have, let us consider the Weyl basis of SLN plus 1 plus. We have generators x1, x2, xn, the set relations which define this Lie algebra, SL plus 1 plus. So this is the relations. A Weyl basis can be defined in this way. The Weyl basis of this Lie algebra, this is nothing more than we have these long commutators k plus 1, xm, where k and m sum to numbers between 1 and n. So this is the Weyl basis. Now let us consider this Lie algebra of type Bn. This is the same generators x1, x2, xn, and we have almost the same relations. This is the same relations with only one exception. The last relation is not xn minus 1, xn equal to 0, but we have here xn 3 times. Also we can construct the Weyl basis in this way. We consider the sequence x1, x2, xn minus 1, xn minus 1, xn minus 2, and so x2. And here xn, the second one, we identify with xn plus 1. Xn minus 1, we identify with xn plus 2, and so on. And so we have here the repeating elements xt is equal to x2n minus t plus 1. And again, the Weyl basis contains on that long skew commutators. But they start here and they finished here in this zone or in this zone also it is possible. This is Weyl basis, the explicit form. Skew bracket. Now I define the skew bracket in order to reformulate this basis for the quantizations. A skew bracket on homogeneous in x1, x2, xn polynomials is defined by this formula. uv is equal to uv minus p, which is a coefficient which depends on uv. Here we have vu. And the point that this is b multiplicative parameter. So we have pxi xj equal to a number pij, and this is the parameters because they define this form completely. Here we have these two natural formulas. Puvt is equal to puv for put. This skew bracket satisfy something which look like Jacobi identity. We have here 3 terms which are equal to the terms of Jacobi identity for color Lie algebras, and here we have some rest, which in some sense is less than the polynomials that appeared here. But here appear the multiplication, original multiplication, which is not, which cannot be expressed in terms of the skew commutator. How to define the multiparameter quantization UQ n plus 1? The point is the following. We consider the Serre relations, and instead of the commutator, instead of the Lie operation, we consider the skew commutator. The only point is that the parameters should satisfy some relation. So in fact, we have just n squared minus n plus 2 over 2 parameters, q and pij. And here we have that pij are dependent. The one parameter, the classical one parameter version appears if we put pi I plus 1 equal to pi plus 1 I and equal q and power 1 over 2. If pij equal 1. How to define multiparameter version quantization of UQS SO to n plus 1 plus? The same, we put here the Serre relations. Instead of the Serre relations, we can see, instead the Lie operation, we put here the skew commutator. We have, again, we need to put this relation in order to define here Hopf algebra structure. So we have these restrictions. Here again we have just n squared minus n plus 2 over 2 parameters. They are independent, but not in sense that they are algebraically independent. They They may be algebraically dependent in any way, no problem, but they are independent as parameters. The one parameter version appear if we put this condition. Also the neighbors equal to q minus 1, Pij equal to 1 if I minus j is greater than or equal to 1. A few words about Poincaré-Birgefit generators. As said, U1, U2, Un is set a Poincaré-Birgefit generator so far if we have that all products of this form, is the basis of algebra. The Q-Weyl Poincaré-Birgefit generators can be defined precisely in this form. We take the Weyl basis and instead of Lie operation we consider this Q commutator. So, and this is also Poincaré-Birgefit generators. And so we take this, the same construction, just instead of the Lie operation, we consider Q commutators. Few words about Grobner-Cherchov theory. Let us consider the set, the ordered set. We order it in some manner this set U1, U2, UN. So they are variables, and we put some degrees di, positive integer degrees, to that variables. Then we can define Deglex order on words. W1 is less than W2 if either the degree of W1 is less than the degree of W2, or the degrees are the same, but W1 is less than W2 in lexicographically. And let us consider an algebra which is generated by these elements and is defined by some relations, fs equal to 0, where s is some set of indices. We may rewrite the defining relation in this form, ws equal to fs, where ws is a leading word of fs, the leading word of the fs. Fs has just one leading word. And so we can rewrite in this way. And this provides us an algorithm, how we can transform each polynomial in the like linear combination of elements of the sets sigma. This is the set of words that have no ws as subwords. And so if we have the word that has no of ws as subword, we cannot apply this diminishing procedure to replace these leading words to the linear combination. And the point is that this set always span the algebra A, but probably this set is linearly dependent. And so the Grobner-Cherchov theory provides necessary and sufficient conditions on the above system for sigma to be a basis of A, to be linearly independent. Now, Pridi, in his famous paper, proved the following theorem. Let W1, W2, Wn are variables with degree equal to 1 with Deglex order onwards. Consider a quadratic algebra. This is algebra defined by quadratic relations. And we may write an equivalent system of the defining relation in this form. Ui, uj equal to the linear combination. Again, we take here the leading term, the leading term. Pridi proved the following theorem. If the above system, if a Grobner-Cherchov system of defining relation for R, then R is a Koszul algebra. This is a fundamental theorem. So, let us turn to the quadratic linear algebras. Here we consider the quadratic algebras. We have quadratic relations. What happens if we consider quadratic linear relations? So we have a set or linear space, linear subspace here of quadratic linear polynomials, and algebra is defined by these quadratic linear polynomials. So we define linear spaces Vi, which is the sum of all Z components. And factorized by ideal generated by R. We have these subsets in A. And so we can consider the graded algebra, which is related to this filtration. So this is the formula, well-known formula, how to define the product in this graded algebra. It is easy to see that this graded algebra is generated by this element, this UI equal to UI capital is equal to UI plus V0, which belong to this factor. E satisfies these quadratic relations, but not always it is defined by that relations. And so the quadratic linear algebra A is called a Koszul if this graded algebra is quadratic Koszul algebra defined by the above relations. This is one. This is the definition of the quadratic linear algebra. So, simplest example. This is, let us take the Lie algebra with basis U1, U2, Un. We consider the universal enveloping algebra. So we have that relations which define this universal enveloping algebra. And the point is that this is the Poincare-Birgeau theorem is equivalent to UL to be a quadratic linear Koszul algebra. Let us consider Poincare-Birgeau generators in any algebra, which is U1, U2, Un, the ordered set of generators. And so, by definition, we know it means that these products forms the set of the basis of this algebra. So, if we take the product Ui multiplied by Uj, then it is also the linear combination of these products. Here, I is greater than j. For example, U2 multiplied by U1. We have these relations. Let us denote this formula by formula 1 because we shall this appear various times. First proposition: if Ui, Uj are the leading words, then 1 is a Grobner-Shestov set of defining relations for the algebra A. So we always have this type of relations, but Ui, Uj in general maybe not the leading term. But if all of them are leading terms in that relation, then this is the system of Grobner-Shestov defining relations. This is not difficult proposition. It's very easy to prove. Proposition 2, if additionally 1 takes the quadratic linear form, it is possible that here we have just quadratic products and linear products. Then I is quadratic linear Koszul algebra. This is also not difficult theorem proposition. This is, we have these two statements. Yamani in 1989 and independently Rosso in 1989 found Poincare-Birgeau generators for this algebra plus and minus for quantization. Yamani wrote this relation for his Poincaré-Birgefit generators in the explicit form, so that UQ becomes a quadratic linear algebra. But Bokuch and Malcolmson in 1996 verified that the Yamani relations form a Grobner-Cherchev system of defining relations. So using all the results, we get immediately that the one-parameter quantization UQ in the Yamani generators is a quadratic linear Cazul algebra. Now the first theorem that was formulated, that in the case of the multi-parameter quantization is also a quadratic linear Cazul algebra. What we do, in fact, I explained the way how to prove this theorem. All we need is to find these relations, relations 1 for this algebra. And that relation has this form. Here we have this Q commutator, but UKM multiplied by URS is greater than all that polynomials, and this is greater than URS multiplied by UKM. So this the second term we can move in this right in this side, and so we will get the relations 1, which has precisely this form. So this somehow this is the table of multiplication, which shows that the quantization is a quadratic linear Cazul algebra. And here we have these explicit coefficients in this form. But for the theorem, it is not necessary to have these coefficients in the explicit form. Theorem 2. This is also the second time we see the theorem that in the case Bn, this is also the quadratic linear Cazul algebra. In this case, the table of multiplications, the relations 1, has this form. Also, we have these coefficients in the explicit form. We have this, this table of multiplication. Okay. What about the case G2? G2 is defined by two relations, G2 plus. This one and this is the second one. In this case, the Poincaré-Birgefit generators has the following form. We have here the skew commutators, and so here should be shown how the product applies. And here we have the normal alignment of parentheses. And this is, we can U2, this is term U3, is this term, and so on. And this is precisely the QL generators in this case. Here we have also the total table of multiplication, but there should be 15 relations. But the point is that all other relations are 0. That's all. But here, just how much? 10 seconds. 10 seconds, okay. But, okay, this is sufficient. We have here two cubic relations, this one and this one. It is possible to cut off these relations. The rest also will define the same algebra. But this algebra is not Cazul. So this is the result. And also, certainly we should prove strictly that this is not Cazul algebra. This is not sufficient just to cut off these two relations. Also, recently there appeared a paper by Vanusa Dilewski, Barbara Pogorelsky, and Carolina Reins. They consider the algebra F4. But they do not consider this precisely problem, but they found the table of multiplication. And this is possible to analyze in the same manner this algebra. Certainly, this is not the end, but the beginning of a new topic of research. For example, if the problem is this quantization a quadratic linear causal algebra for these quantizations? Thank you very much.
G2 is or is not?
G2 not.
It's not quadratic linear.
It's quadratic linear, pero not quadratic linear causal algebra.
What happens if you take the enveloping algebra of a super Lie algebra?
I cannot answer immediately. I think it's the G2 or the general case.
Just a Lie superalgebra without quantization.
It's of course it is quadratic linear causal algebra. Yes. By the same, because we have this relation absolutely the same like in Lie algebras, just with coefficients. Certainly, yes.
And for quantum versions?
Quantum versions, I don't know. It is necessary to consider. But I think that it is also true because we have parameters and we can organize these parameters in such a way that they repeat this quantization. Parameters are independent. I mean not algebraically independent, this is very important. They are independent, I mean that they can take each value.
Thank you.
You said that this is not linear, it's quadratic linear but not causal.
No, not causal.
This is the case of G2. It was not clear for me that you said that you don't use the convex of you need to do more work. You say you put the relation, but from the relation you obtain the result. You need to work more? Or?
I take the generators.
The generator,
yeah. The relation is not so important. The important are generators. The point is that each algebra is quadratic linear causal algebra if we consider a set of generators the basis. And the point is that we found this smaller set of generators in order to call them like quantum Lie algebra. And this is our point of view.
Any other question? Comment? If not, we thank the speaker again. So the organizer asked me to remind you that tomorrow we start at 9:30. Okay.